So is the screen visible to everybody? Is it like big enough? Back. Okay then. What? It's clear enough, right? Okay. So for the you can see. Is it big enough now?
You don't see it. On the night, now why?
So for the GKR, it is like you can't see it. How is it now? This stuff is lagging, so I didn't know how much it has done. You should calm down. Okay. So
before you start, can you go up? That some check that you're using, do you?
this one check. This one.
Yes, that's where you coming from.
This is my normal sum check that I adjusted to work with GKR, yes. So when I get to where it comes in, I'll go there and explain it. So the main goal here is just to create a proof, and then the verifier should verify it. You can't hear me.
You can hear me, but
Can you hear me? There's nobody at the back at the last page. Frankie, can you hear me? Okay, so there's a proof struct that is holding all the stuff there. So the first one there is the output poly. Remember our circuit, the W0, yeah, that's our output poly. And the polynomials, those are the unipoles we get from the sum check. And then the evaluations also, that's the evaluations of WB and WC that the verifier requests for after each round. So those are the three things that I put in my proof. This may not be the best way to do it, Shabo. Well, I believe it works. So now for the proof, the prover knows the circuit, of course, and then the input. So he wants to prove that he evaluated the inputs correctly. He evaluated the circuits correctly. So start with our transcript, since we're trying to make it non-interactive, and then circuit evaluations. So this is me actually evaluating the circuit here on this line to get my output, which the W0, W1, blah blah blah, for the number of layers that we have, and then W0, that's the output layer itself. So what I'm bringing out W0 is we need to check if there's only one value. If our circuit has one output, we need to add a 0 to it to make it a valid polynomial and evaluation. Yes?
Why does your transcript have months back in?
It is, that's the inferred type. So that month backend is this FP month backend that's the FQ type. So yeah, and then transcript takes, so it's something like this. It's meant to be like this actually.
Download original.
If that I typed it myself, it has been like this. Like if I give it, if I specify the type, Roma. So this is that type. So FQ is the something FP month backend. Yeah, that's where the month backend thing came from. So
that claimed evaluation is your WB and WC, right? WRB and WC.
yes. So if the output is 1, we add another 0 to it to make it valid. So that's the purpose of this check. Yeah. So and then I'm turning to an output polynomial. Sorry, I'm turning to a multilinear polynomial. It's just in the evaluation form. So with this now I can start the protocol. So I have a function called initiate protocol, and the reason why I put it in a specific function is because both the verifier and the program are doing the same exact step. So let us check what that one does quickly. So it takes in the transcript and then the output polynomial.
That's the minute.
Yeah, W naught. So what the main thing this one is trying to do is create our M0. Remember our M0 is yeah. So the way the protocol starts is the provider will get the output poly and then send it to the verifier. Now the verifier will pick a random value and evaluate the output poly at that random value to give us our M0, which is like our first claim sum that we are going to start with. So both of them are going to do that process, since this is like a non-interactive this thing. So that's just the main thing I'm doing here. So I'm appending the output poly, the evaluations from the output poly, and I'm using that to generate a random challenge, which I'm now evaluating the output poly at the random challenge to get the M0, and I'm appending this again once more. I'm appending the M0 again to my transcript. So for the next round of encrypting or generating any random value is going to start from my M0 being there currently. So and this is returning a tuple of M0 and that random challenge. So we actually need it. Yeah, in the proof. And the verifier to also need that random challenge also. But that's like our RA. Remember our add die and more like I already evaluated that A. But when we get there, so back to the proof. If the event is not clear, please ask as I'm explaining. Or if I'm doing anything wrong, also stop. So yeah, I'm getting number of layers to know what I'm running my circuits, what I'm looping over. And then the polynomials, this is just me instantiating the empty vector. What's that?
Like, I think I missed the step after we came back from
Okay, no, it's just I haven't done anything. I'm just initiating some values that we use later on. Like this number of layers I'm using to calculate some things so that the size of the vectors that I'm working with.
But we can't hear you.
You can't hear me. But you were hearing me before, right? Like, did you hear the initiate protocol thing? You can hear me? How come? Frankie down there can hear me. Okay, is it better?
It's not.
Exactly, please. Okay, so the proof police, those are the unipolice that we're going to get from the sum check, and then these claimed evaluations.
Which you're the one that collected down here. It's capacity for your
No, it's a default this thing. So it's just a normal. Instead of doing vec new,
Yeah.
if you give it like the capacity, it knows the whole size of the vector, and then it doesn't need to like recalculate the size of the vector anymore. So it's like it gets optimized from there. So this current RB and current RC is just to hold our current random values. Where I get to where I'm actually keeping them out, I will explain the reason why. And then our alpha and beta also, which will come in later. So what is it?
I think we're already getting off on
No, we've not started using it, it's still 0. But where it comes into play, you will know by the time you get it. So because of the way me I'm evaluating my own circuit, I needed to reverse it. So this one it may be different for you guys, I know. So my layers to also needed to also reverse this one. So like first second then reverse. And now this is where the whole work now starts. So we loop through each layer. We loop through each layer, getting the W poly for each layer. So now the W poly is the evaluation of the next layer. Remember, the whole purpose of the sum check is to, or not just the sum check, the whole purpose of proving is we're trying to prove the layer above with the layer below. You get it? So W poly is just, that's WI plus 1 in theory. So the way I do this is, that's my index.
Oh,
So index and each layer
okay.
in the layers. So remember for the last layer, that one does not have a WI poly. WI poly for that one is the inputs. So yeah, that's why I just did this check, like if
If
if the index is already the same as number of layers minus 1, like if it's on the last, this, this is the index and the length is 1, is the index plus 1. So if it's already on the last layer, that's what this if statement is checking, then use the input as WI poly. If not, take,
oh, you're only considering your input.
yeah, if not, take the circuit evaluation for, that's WI poly for that particular. My circuit evaluation is coming from here. Remember, I evaluated my circuit at the start
Okay.
with using the inputs. So yeah, and then
Sorry.
yeah,
Please explain this last layer
which one?
using the inputs. This one that I just,
This one.
yes, like, I don't know if it's
Okay, so yeah, I'm trying to get the W poly. Your W poly is WI plus 1. So that's the evaluations from the previous, from the round, yeah, the round lower layer, sorry. So I'm first checking if the ID is the same, if the index is the same as the last layer. If it is, then I'm using the input as the W poly, because that last layer does not have a layer below it. The inputs are the W poly for that
so
one.
let's say you have 3 layers and
Yes.
your index starting at 0.
Yeah, that's the first one.
0, 1,
2. Yeah, that was minus 1.
okay.
You know, the length will be 3.
Yeah. So like, is your input, like your input, are they part of your layer in the circuit?
No. So yeah, this depends on how you people implemented your circuit. If your input is part of your evaluations, then you won't need to do this actually. But me, for mine, is not part of it.
Okay, that's why you have to.
Yeah, that's why me and just do. Yeah.
I think your input is part of your layer. If it's not part of your layer, you're not supposed to do -1 there.
No, it's not.
Eh?
It's not.
It is, because the reason why you do -1 is because you want it to loop through your layer, excluding the last one.
No, the reason I did minus, I understand it, but the reason why I'm doing minus 1 is that example she brought now. If the circuit has 3 layers, then the length is 3, but the index of the last layer is 2, not 3.
The index
Of the last layer is 2, not 3. So as I'm doing 3 minus 1, 2.
okay, yeah, I get it.
Yeah. So is there any, Roma, is it,
Yeah.
you understand now? Is there any question elsewhere so far? Okay. So after that, after getting our W pulleys, we also get our FBC pulley. This one to also have a check there. For the first one, the FBC pulley for the
Yeah,
output, yeah. Alpha and beta are not being used there, right? So I have a different function together. I'll go to it now. Then after the output poly, all the other layers are already already have alpha and beta in them, so that's why I have like a get meshed FBC poly. So let's quickly check those two. So my normal get the FBC poly it is getting the random challenge. This random challenge is the first one. That's like RA, and then the layer also WB and WC. Those are the two. You guys remember the formula or just the structure of the FBC polynomial, right? Add die, yeah, add die plus times more like. You guys remember that structure? So yeah, that's exactly what I'm trying to do here. So first, this one is getting my add die for that particular layer. The implementation is in circuit, so I'm not explaining the circuit part, so I may not go to it. Then I'm also partially evaluating at the first random challenge at the first bit. So remember our add I does not actually, it is add I evaluated at A already. Are you guys clear with that? Are you guys, is it clear?
Yeah, like ADA is normally add A, B, C.
Yes, at A. Yeah, so that was.
Is everybody clear?
So yeah, I'm doing the same process too for my.
How you put it? Yeah, you're not following. Be like so. Right?
Yes, sir.
How you put it? Jeremiah. Sam. Say you put it. Favor. How you put it? Like any point that is not making sense, ask. Right? The essence of this is that by the time he's done, everybody understands what he's doing. Right? And you should be able to go back and implement. Right? So you don't need to implement what's implemented. If you understand it, you implement it the way you understand it. Right? So what it's doing is just to help us get an idea of what exactly it's doing, so that when we want to implement, we know exactly how to go about it. So if anything is not making sense, please ask.
So I also repeated the same process for Molai. I got my Molai for that layer, and then I evaluated it at 0 with the random challenge. And then the next one is getting the W pulleys added together and the W pulleys multiplied together. So our W pulleys are actually the same thing. Like the WB and the WC, they're actually the same thing by the time you start solving it. So this tensor add that's the blow up thing. Yes, that's it. So I just add them all. It does both of them without the two. So it takes in two polynomials and then the operation. Are you adding or multiplying? And then it returns back a multilinear polynomial.
Sorry. Sorry.
So it is looping through the method I used is this tensor, this thing I didn't do the blow up. So it is looping through the first polynomial, then for each value, for each one to multiply or it will add whatever the operation you are doing. It will deal with all the values in. So for each value from the first polynomial, it would either add or multiply every other one in the second this thing and then just collect it and know. Is this tensor add and mod? Is that one clear? Is that clear? Okay. So the way it is normally is we're meant to like blow up those two. Huh? Maybe. But it is not connected to your system.
Yes.
I'm going to like be switching to
So to be switching to now I have to maybe if you just finish it, you can just stop sharing.
stop sharing.
Just so that it doesn't take over the screen totally.
So let us assume favor. Let's assume we wanted to add two polynomials now. Let's say 2ab plus 3bc sort of. Let's say we wanted to add these two together.
You don't need to go into it.
Okay.
You understand? So just draw and arrange.
Okay. How do I Okay. So let us work with the evaluation from them. Let's say we had 0, 0, 2, 4. Let's say we wanted to add this polynomial to 0, 2, for instance. Even if two of them were like the same length, these two guys were the same length, they have different variables and no. So we still need to like make all of them equal. So this was an evaluation from that already, like let's say that one would have added plus 0c to the first one, then to the other one would have added plus 0ab. So all of them be equal, but in evaluation form we blow it up to account for those new ones. Yeah. So but this implementation I did there is not blowing it up, it is doing tensor blah blah blah, something like that. So the way it works is each one from here, if you add it to everything here, this one too, if you add it to everything here, and then give a new array of 8 variables. Same thing for multiplication. If both of them were 4, 4, it would be 16. Let's say both of them were like 0, 0, 0, 2. Let's say times 0, 0, 0, 3. It will be 16. It will take each one from here, multiply everything here. This one to multiply every single thing. So that's basically what I'm doing here. This. Yeah. So yeah, that's what.
To make it easier to. I think that should make it easier to switch.
Okay. Okay. So that whole process that I just showed now, graphically, that's what is going on here. So the way this works is, it is iterating over the first one, starting with the first polynomial, and then it's picking each point from there. So with this one, it iterates over the second one again, picking each point there, and then it multiplies one from A with B. So in normal loops, it will be like for I in this, then under that one for J in this, then I times J, that kind of stuff. So is this process clear?
Yes, sir.
Yeah, and then this flat map and move some Rust things. Let's not go into those ones. But what is going on here is sharp clear. Alright. So now back to where we were before. We're talking about the FBC polynomial. Yeah. So this one sums up our WB and our WC. That's this one here. And then this one multiplies the two of them together, which we use in our product poly. So our product poly is a struct holding two multilinear polynomials that if they multiply together, they will give a non-multilinear polynomial. You get, so that's why we're like holding them separately using that product poly. So we put in I put in my RDI, the evaluation forms, and then the summed W polys. Same thing too for the other parts with more life. And then I have a sum poly struct that is holding those two product polys. And so this entire structure, this sum poly itself, that's the FBC polynomial. Like that's just the whole process going on here. Is it making sense?
So this is the one that does your new, like gets your new FCC polynomial. This is the new RI and new molar.
Yeah.
This is the alpha and the beta.
Yes. No, this one the one using alpha and beta.
This one is not using.
This is not the one using alpha and beta. This is the one using alpha and beta, yeah.
Okay.
This is the first one that works for the output layer.
Yes, I thought
Where
this was inside that layer.
I didn't put so many functions on my stuff. So but just to be clear, this whole part clear to everybody. Levi, is it clear? real. This one is so in the. Let me just show the structure of the FBC polynomial. So So our FBC polynomial has this structure. Add I. This add I is evaluated at A, but for now let's not concern ourselves with that. Times WB plus WC this times mol I times WB. Oh, it's plus.
Yeah, that's plus.
Sorry. Plus mol I times WB times WC.
Plus.
No, this one multiplied.
Yeah,
This one that is added. So you this is what that sum pole is holding. It is holding this entire structure. So now each of these guys are product police. So since if we were our addi has B and C in it, this ones to also have B and C, both of them. By the time we add them together, it will be B and C in both of them. So if we were to multiply those two guys, it will give us B square, C square, that kind of thing. And we don't want to have that. So we're adding down in a product poly. I'll still go back. I'll still show the code, but I'm just like trying to explain the whole thing. So now our addi is there. These two guys, these two guys that I summed together using tensor addition. These ones. Then so I multiply these ones together using tensor multiplication. And then I now multiply. I didn't multiply, I just put it in a product poly with this one. So these two guys are in one product poly. These two guys are in one product poly also. So is it getting clearer? Yeah. So then these two together make up the sum poly, which is the structure. That's the entire ABC polynomial itself.
You want to switch? You want to switch? No.
I'm coming for you.
Let me just undo.
Okay, I can switch from here there.
So you can switch.
I'm really saying for yeah. Yes. For the entire polynomial. ABC for the entire. I said that.
This ABC is for which
It's for a layer.
or for a single layer.
Yes.
You have
So each layer has
different
its own
ABC
ABC polynomial. Yes. Yeah. Okay. So yeah, this is exactly what I was doing. So this summed W poly, those are the ones in the addi part, the ones that I summed together, WB plus WC. Then this multiplied W poly, the ones that I multiplied together, WB and WC, they multiplied together. And then this is now bringing them together in a product poly, the addi and the summed and the summed poly, then the mol line and the multiplied poly. Then putting those ones to again in the sum poly, which is the FBC polynomial itself. So this is what this function is returning. This gets FBC polynomial. This is what, so is it better now? Okay.
I want to be sure.
So remember our W poly is coming from here. This is where we are getting our W poly from. It is the evaluation on the layer below it. So now for layers that are not the output layer, alpha and beta would have already come into play here. The reason why we are working with alpha beta now is in the process of our sum check, the prover wants to check if FR1 R2 is equals to FC R2, and to calculate FR1 R2 he needs WB and WC, like the evaluations of WB and WC. Sorry, that's the polynomial. Like, should I say polynomial from another layer?
If you want to,
Huh?
if you want to write, just
Okay.
tell me.
Okay. It is just a part of the process of checking this thing, of in some check itself. Maybe I should just use this one to explain the sum check part. Okay. Yeah. So after I will still explain it, but for now let me just get this one out. So the prover at the end of the oracle check in this one is checking f elevated at r1 and r2 is equals to fc evaluated at r2.
Yeah.
This is the final oracle check that the verifier will do. So the verifier can do this since he has fc
Yeah.
and r2, but he can't fully evaluate, he can't fully compute this one because to do this one it is add I w for that layer uh, plus the more like this one. So it does not know that the w values on that layer. You know, the verifier does not know the intermediate evaluations. This he knows is the circuit and the output and the input, but the intermediate. So he would request those things. So request w being w evaluated at r1, sorry, not w. You're going to request w evaluated at r1 and w evaluated at r2 from the prover. So now this w is for the next layer, but now there are two new claims that I don't trust. You get. So we also do some checks on these two new claims, these two guys that the prover gives to him. It can be correct or not, but he does not trust it. So you also need to perform some check on it.
Can just draw like just a random
His circuit. Okay. So let's say
drag it.
Hmm?
Drag it up.
okay.
To erase, you can just press and choose.
So let us assume the circuits we're working with. So we first start with this layer. This is our W0. Right. We perform some check on this one. And then to construct this FR1 R2, it needs this W poly. W poly is coming from the next layer, the layer below, evaluated at R1 and R2. Now the verifier can't compute that one, so you request it from the prover, which now sends it to him. You send W evaluated at R1 and W evaluated at R2, which are two new claims. So he's going to use that one to compute this and then finally verify if this holds, if these two things hold. So now if it is correct, it goes to the next round. And that next round is performing some check over these two new claims. But there is a problem here. If we do 2 now, for the next layer it's going to become 4, because there will be 2 for each one. And then let's say we had a bigger, it will keep it like exponential. So and that would be expensive, and so instead we merge it together. So these two are going to merge it into one. That's where alpha and beta now come in. So is the whole FR1 now 2 thing, is it somehow clear?
This F1R2 is going to be done like for every subject.
Yes, that's the so there are like 2 oracle checks,
Yeah.
but it's only doing one actually. So like there's one oracle check in the sum check itself,
Yeah.
and then the final oracle check in GKR.
But
But
you
you can't do the oracle check in this thing exactly. So that's why your I will still, when I get to some check, it will maybe now it will get clearer. So when you are verifying your sum check, you are going to return something that can be used to calculate this. Like you return your 2 challenges and your FC. Your FCA at R2. That's what you are going to return instead of you returning maybe true or false, which was the normal sum check thing that we did. So I don't know, what part is You see how we come about this. Remember normal sum check. Yeah. We are trying to prove that one polynomial it was summed correctly. So in that process, we after we do that whole thing, we do a final recall check where we are going to work with the original polynomial. We are going to evaluate the original polynomials, all the random challenges that we worked on, and then we're going to check if it's equal to the last unipoly evaluated at the last random challenge. So that's still the same thing that is happening here.
Okay, but what I don't get is, I understand that you have initial layer polynomial, the F R1 R2. That's one that has the RI, MOLI, W, and then when you have that, the verifier will have a second random point, a polynomial that is a second random point that's supposed to equate whatever you get from evaluating the entire layer. Right?
Yeah.
We're not saying that the verifier does not have a second part of the equation to compare against.
Yes, something like that.
Right.
Yeah, something like that.
Because it has a side and it doesn't have.
It doesn't have
side.
some of them.
It
Yeah.
doesn't have so what are you passing? Like you're saying that you're passing the WR1 back to the verifier. Is that what you're saying?
Okay. Let me understand. So now this FR1 R2. Let's check if it is equal to the or to this guy FCR2. Now FCR2 is our unit is trying to be output poly evaluated at R2. It's still they're meant to be like the same thing. So this one is also like trying to do the same thing the verifier did, the prover did, sort of like trying to check it using the layer below. So it's trying to say, okay, if the layer below evaluated at these two guys is equal to this one evaluated at this, that means that whole part was completed properly. So for this one, you also construct an FBC polynomial, something like that. But you don't really need to like in implementation, you don't need to like construct the FBC polynomial. But that's what the verifier is trying to do. Trying to construct an FBC polynomial. That's what this. So this FR1R2 is an FBC polynomial evaluated at the first random challenge. There is one random challenge that is not being written here. So let's say R0. Check if the FBC polynomial evaluated at R0, R1, R2 is also equal to FCR2. FCR2 is the last unipoly evaluated at R2. So now to construct this FBC polynomial, that's where the whole WB and WC will come into play. It's just the same thing, which E can't do. And then he asks if you send the two random challenges to the prover and then tell the prover to give him the W poly evaluated as the two of them. Yes, those two random challenges. So once the prover gives him, he can now complete it. He can now do this FR0, R1, R2, can complete it, and then can now compare the two. Is it equal to FCR2? So that's like your equal check.
Sorry, so the point is doing the work of the program, and just like giving it the value.
It's not the work of the prover. You don't calculate it, you don't compute anything. That's like when you get to the implementation part, you don't need to. So this is going to be a value on its own. It is not a polynomial. Like by the time you compute this, like you are working with all the evaluations. So it's not good. You are not going to get the verifier is not getting a polynomial back. It's going to get a value. So you're going to just check this value is equal to this other one. That kind of stuff. So yeah. Yeah.
Seems to not sure.
Let me stop sharing. Okay, I don't need to stop sharing this one. Oh, because I joined, it became a normal call,
Okay.
which is ending soon.
If it ends, we're going to
Great.
share it. Or should we just end?
No, we still have like 12 minutes. Still have like 12 minutes.
Share it.
So, but for everyone else, is everything clear so far? Joshua, Frankie, is everything clear? Superman, is everything clear? Okay.
Just passing, it's fine.
No, you were paying attention now. Is everything clear?
I think they pay attention, people not clear.
Okay, is it clear?
Small.
What part?
I want to ask because I don't know if it's the same, because I'm kind of like using round pulley.
Don't let the naming. That mostly the same thing. You mean
That's the
pulley,
same
round
thing.
pulley. Yeah.
No, I'm using round pulley instead.
It's the same thing.
Okay.
Just choice of name. Okay. So yeah. When we get to the second round, I will explain this game matched FBC polynomial so we don't like, or should I explain it now? Why?
Yes.
Oh, I don't want connected. Okay. So yeah, I was saying after the loop, like when we get to second round, I will explain this gets merged FBC polynomial. Or should I explain it now? Which one do you guys think? Or I get to where alpha and beta actually come in, and then I come here.
I still the get
Hmm? We should just explain it now. Okay. So if you guys remember the first normal get FBC polynomial, we are just taking our layer and then the random challenge. So favor this random challenge, this first one, that's that R0. That's like the first random challenge that we used to compute our M0. You know what M0 is? So when the the initial case one, when the protocol starts, the prover will take the output poly and then send it to the verifier. Now the verifier will pick a random challenge. That's random challenge. Now you pick a random value and then evaluate W0 at that random value to get M0. So that M0 is the first claim sum that we start the whole thing over based on check over. So that was the first. That's absolutely. But in the next round to change, like in the coming rounds, M0 and the random and that random round they will change. They will be new. They will be new values. So yeah. So in this first FBC program, so this one like very straightforward. We got the add died and the more like for that layer. We got the W police for the next layer. We sum them up, multiply them, and put them in our sum poly. Now in this one now we have alpha and beta. This one we're trying to merge it. Remember the reason why I give for us merging, right? This side, everybody's DK.
Is everybody
I
following?
follow.
What's part is now?
Yeah.
What is it? What is it? Hey.
So it's something different.
Oh, yeah. Favor. Peter. I forgot. Sure. Any question? Well, like, the essence is to understand the flow, right? So that it will help you when you go back to the goal, right? So just try to follow first, understand the flow, so that you can know where like exactly the goal is coming from. Okay? DK.
Okay. So the reason why I gave for us needing to like bring in alpha and beta, and then is want to perform now want to prove that our W divided R1 and our W divided R2 is correct. That's like that's the next layer. I want to prove that next layer was evaluated correctly. So we want to get an ABC polynomial this time. Well, normally, no, in normal sense, we were meant to like get two ABC polynomials to represent the two of them. Like Adamolai, WB, which would be like two, W should be WBs from down now again. And WBs like that's what it's meant to be normally. We get one for W evaluated at R1, we get one FBC polynomial for W evaluated at R1. And then we get another FBC polynomial for W evaluated at R2. That's the normal. Eh? What is it? Yeah, R1 R2 is the same thing that so that's the normal thing that we're meant to do, but because that would be a lot of work for both the person and the computer, we introduce two random values, which are our alpha and our beta, and then using that one we can merge. We just need to like create just only one FC polynomial to represent the two of them. So the way that works is, let me show a little bit of. Huh? No, not switching.
Okay,
Let's like open one of the documents at the same point.
Okay.
Maybe people should maybe be on it. So now when we do that, we also actually no, not switching. We also do this same thing. We do it for the claim sum also, for the next claim sum. Like we also need to like merge the two of them together. That WRBC and WRB and WRC. We also need to like merge those two together. So now I want to prove that our ABC polynomial. No, you can do it. You can do it without bringing in alpha and beta, without merging it, but it's a lot of work. That's the input. That one is still that's the last final layer, but we can't jump from that one to that place. So we need to do each intermediate layer till we get to the input layer. Yeah. Okay.
And then using the RB and RC to compute WRC. But we don't understand WRB and RC and whatever, they're used for the MRI. How are you using the
Ada they're part of the ABC polynomial.
Yes.
Same thing as the WRB and WRC. It is also you also calculate it with your you also calculate it with your what's it called? You calculate your ABC polynomial. But let me try to get your question again. Right?
So now I'm seeing get merged FBC polynomial.
Yes.
And I'm seeing that it needs WC,
Yeah.
which is going to be WB probably validated at without the alpha beta whatever. WB is going to be validated at RB, and then WB is going to be validated at RC. Right?
Yeah.
But we're trying to, he said yes, we're trying to use something, I think the alpha or beta to replace, is it multiplication?
No, don't replacing anything. So the thing is for
Let's just
okay. I'm going to explain to you, but fine, go and get the water. But so far, does anybody have any question? Before we resume, any question at all about the GKR stuff? What bug are you facing? FBC. What about the FBC? Yeah? Data. That's nice.
So this
What if someone is facing the same bug? We're talking about FBC now. That's what we're
It's a different way of implementation. So based on my own implementation, I can't tell explain to you. Except to see the code.
no problem.
I think you're supposed to
Lovely.
join the meeting.
Oh,
No, I don't think so additional implementation. The major issue now is from my online.
From the
I
other.
did fast. I did it fast when I did evaluation. So now when I'm trying to test it, it's not very fast. But if I pass in the layers, the different layers, it's normal. But when I evaluate it, it's really fast.
And I see you.
Like
No,
your input
passing
layer
the-
is
Alpha,
there, so
beta, lactam.
Yes.
your input layer is there.
WRB
No, my input
plus
layer
beta,
is layer
WRC.
0
It's
for the circuit.
the prover that does that.
But when
refer
I
to
pass
also do it.
I don't know if you get this now,
Refer
because
to
it
the
looks like you have
The last
you
layer.
verify 3 steps.
Refer you also mentioned.
But it shouldn't be, right?
That's
Yeah, I was
You
thinking for
verify.
the outside.
yes, the verifier. You know that FC evaluated at the last one or so much. That's like the one case that is supposed to do the checkpoint. And if he does alpha beta too, that's another one. And then it will
Alpha and beta are not claim summaries. They are random values.
when you do alpha like WB plus beta and
That's the next claim summary. Verify will do that. Verify will do something like that. That's to know. So the verify wants to check.
because that's basically sent to it like
I think he has to take it into account
okay,
that random values are here now. He has to take it into calculation. So you get. Okay. So your favor was what's your question again?
WRC.
Yeah.
You said people are using the alpha beta in that
Okay,
situation
what are you using
for,
for?
yeah.
Am I going to share now? Yeah. Why are we using WRB and WRC for in that equation? Okay. So the normal thing was we were meant to like perform, we were meant to write an FBC polynomial for each of them. Wait, leave Adam alive and the W police alone for now.
Sorry, because my understanding is that FBC polynomial
As okay, yes, it is Adam like plus.
multiplying against WB is
Yeah, that's the FBC polynomial. So yeah, we meant to have that stuff for both, for the two layers, I mean the two new values that we just got now.
yeah.
That WRB and WRC. We are meant to have FBC polynomials for the two of them.
Sorry. What do you mean for the two of them?
For okay.
You get because the WBC and WB and WC are supposed to go together to form one FBC polynomial. So I don't understand what you mean by having two FBC polynomials for W. I don't really get.
I get you. Oh, let me. Is it? It's possible.
That's all right. Okay. I'll just
I don't. Let me see if I will explain that one well or maybe fancy. Well, let me just try. Okay, as you joined already.
yeah. This one is not showing. I don't know which one then.
Let me try to share for you.
It's meant to be showing. Like, are you sure?
I'm just starting to share. Okay. So now we have we have a W pulley for we have WRB. W evaluated as RB and W evaluated as RC, which is this W1. So we have W1 evaluated as RB and W1 evaluated as RC. That's what the prover sent to the verifier. W evaluated as R1, W evaluated as R2. This one.
Anybody I want.
Any of the layers.
Oh,
Hmm? Okay.
Not for the
W,
first.
first of all, is the evaluation of that layer.
Yes. So the evaluations on this
The
layer.
evaluations, what do you mean by evaluation as R1 and R2?
Let us quickly let me quickly add something. Let's say this is let's just say this is our input layer actually. This is the input. So let's say we have 1 year, 2 year, 3 year, 4 year times plus, right? So now if we evaluate it, this is plus, this is going to be 2, this is going to be 12, sorry,
7.
yeah, it's going to be 7. So the W poly for this layer is going to be 2 and 7. This is W1, 2 and 7. So we're going to evaluate this one at RB, and I'm going to also evaluate the same one at RC, where RB and RC are the two random challenges the verifier brought up while doing some check. So from this we are going to get two different values when we evaluate at RB and evaluate at RC.
Also, we get two different
Values. Yeah.
Let's say
It's
if
like-
R,
because
if R B was 0, right? Then if we evaluate this W1 at RB, we will get 2, right? And if RC was 1, if we evaluate this W1 polynomial at 1, we will get 7. So those are the two different W's basically. Yeah, so those are the two different W's.
Let me expand this. Want to see what I can.
Does it make sense?
Yeah.
Sorry, I'm very
But then you disconnected.
Because of the phone.
sorry, it's back on.
Yeah,
right?
it's back.
Okay.
So now, this W1 is still going to be the same. W1 is 2 and 7, right? So we're evaluating. Let's just say if we evaluate that, if I turn this into a polynomial in the coefficient form, it will have just one variable, 2 points. It will have just one. That means if we evaluate that one value, we get is a full this thing. Like we can't really partially evaluate this guy. Right. Now on this next layer also, our RB and RC return to RB1, RB2, RC1, RC2. This next layer will be is going to have 4 values. It's going to have 4 different distinct. and then there will be, by the time we've ruined the first random challenge. So if sorry, anyhow, sure, if you ever that R1, RB1, and RB2, you also still get a whole value, like it is still like full evaluation.
So that means I think this evaluation based on number of dates.
Yeah, on this layer it will increase. So on this layer the random challenges will become 4. Is it for it shall increase, sha? If there were more, they will keep increasing. But can you remember how we did it in productions form? Like if we were to create an FBC polynomial for this layer, for this W1, we are going to have something like this. It's going to be F this into A B1 B2 C1 C2. So now these are our B and C. Those are like the inputs. Even it already become 2 each.
In the number of dates.
Those are the number of bits. So next layer to be like B1 B2 B3. That kind of stuff. So you actually keep increasing. A2 will even increase at some point. It will become A1 A2. You get everything. The deeper we go. So in implementation, it is the way I did it was I left my RB and RC as even the main random challenge, the A itself, as arrays, vector, whichever one. So, but yeah, for when we get to implementation, but for now, is it be clearer what WB and WC are doing there? Okay, is it?
Oh, yeah, okay, yes, kind of. That means the alpha beta would have only applied for layers that have more than one bit. The alpha beta will apply for layers that have more than one bit.
It's really applied to this layer, to the FBC for this layer, which is reduced to these other ones. When you want to construct the FBC for W1, you would alpha and beta would have already started coming to play. So it's going to come in for all of them, starting from W1. Alpha and beta will come in for each of them. Okay, there was something that came to my mind as you were asking now. So the first one is this polynomial, this W1. Let's like the example, the way you explained, W1 evaluated at 0 will be 2, W1 evaluated at 1 will be 7. So I want to prove that we actually calculated those two correctly, that 2 and that 7 correctly. Now we will construct one for 2 using these guys. We'll construct another one for 7 too using these guys. But in the normal sense, it will be an FBC polynomial. But in normal sense, it's meant to be this whole layer for this layer, you get. But we constructed this one from these two guys, right? So we are still going to like treat them like individual gates in the layer itself. In this layer, we are going to see like there are two individual gates, and you want to prove that you evaluated those two gates correctly. So, but instead of having two FBC polynomials, you can merge it to have one FBC polynomial, which will be that FA B1 B2 C1 C2. But we don't want to do the whole C1 C2. We will still do the B1 B2 thing at the end of the day. But is it getting clearer? So this next layer too, we also let's say this there are more layers. On this layer, we also want to prove we evaluated this one correctly, this one correctly, this one correctly, this one correctly. So that's what I was saying. Like, it will become 4. We have needed 4 FBC polynomials at this point if we didn't merge it. But because I'm merging it, we just need only one also again at the end of the day for this old guy. So let us come back here. Please, if anybody gets confused at any point, please just ask. right. So we're looking at Likis, you asked one question. Yeah, something. That's why I told this stuff about alpha and beta.
Okay, the round checks, right? The layers check. Okay, that's it. As you said that you did the. Can do it.
Or maybe let's continue. Maybe if the question comes
Okay,
back.
you answered it already.
Alright.
Not clarifying.
I can't remember what the question was, but if you remember, or if I remember,
Yeah,
I
I
will
was
go on
thinking
it.
about round the layers check, right?
Okay.
For every each the W of the previous layer got you to get the FBC of the next layer. Right, the alpha of WI, WB, your WC, beta WC got you to get the FBC of the next layer. I'm not asking about like do the check at every layer.
Okay, yes. So now you're trying to get the meshed ABC polynomial. These are for layers where alpha and beta are already coming. So as usual, we get the normal the add gates. Sorry, I said the add gates. The add and the multiply. We will get those guys. Are you guys following? Peter, MJ, Mitch, are you following? Young Patience, are you following? Rema, are you following?
Yeah.
Okay.
So, so that I need to do check at every layer, right?
Yeah.
So I'm going to be doing the alpha, evaluate the alpha beta, alpha WI, RB of the RB, then
That's what I wanted to show
beta
this stuff.
WI, of C. Then
That's
I'll
right.
take that is
No.
equal.
Actually, this is what I wanted to show. No.
You check that the alpha, okay, I used to use this. I used to
Yes, no. Yes,
do you add alpha WI of alpha W
alpha times WI, WRB, okay.
plus
Al-
beta
Times,
WIRC.
yes.
Evaluate that, evaluate them, calculate them. You check that is equal to.
You're
I think
going
it's
to
going
check
be the last.
the FBC that has alpha and beta in it is equals to Alpha.
Not just at the last layer.
Yeah?
I think that every
yes,
Check
every layer.
Check at every layer, not just at the last layer.
No, the last layer itself, the check there is just it's the same thing.
Yeah.
But this one you're using the inputs for the last layer. It's still the same process I do not through. But instead of requesting instead of requesting those W police exactly from the prover, the verifier can beat himself now using the input layer.
Okay. I try assuming that the only time you check is at the last layer because I thought that was the point of the reduction. I didn't need to check because
No.
the only event the prover only checks at when he has the W's.
Yeah, you are requesting.
That's
That's why you're requesting for the W's for each round.
But who is wrong the last layer?
Eh?
I thought that if it's wrong the last layer, that
No,
means.
so that last layer, he cannot compute that one himself. So, but it's still possible that maybe along the line, the prover was still dishonest somehow.
Yeah,
But he was still able to still
Get
keep
something
passing.
correct at the last layer.
But if those inputs now, if the input he has with him, if he was to request again, the prover could still send forged inputs. But this one, you're going to use the inputs with him. So that input you can take it like maybe as that commitment kind of thing. Like, if these inputs still evaluate to the layer above, then it means the other ones were truly correct. That's when you can like actually accept it. Instead of requesting, if he was to request the input, the verifier could just send forged stuff to him again. You will accept all the same.
Okay.
Okay, so now after getting our Ada and Molai, we want to do want to bring in alpha and beta into it now. So the way to calculate it, it becomes something like this. Favor, are you following? So yeah, this is the our alpha times RB. Thing is that there'll be two let me add this one. Okay. Why do I keep forgetting not to log this guy? No. Yeah. Let me put this somewhere. Okay. So what was it? I was not paying attention, so
No problem. No need to write it down.
yeah, it's something to save my phone. Yeah, I want to show from you. So when the verifier is it prover that picks alpha and beta? Who picks alpha and beta?
There's a verifier.
The verifier.
But prover samples from the transcript.
So when each of them pick alpha and beta, the prover the prover sends WRB and WRC to the prover, right? So when he picks up, when the verifier, and this is the verifier, when he picks alpha, you also merge these two W's. It's also going to merge two of them together also. So you're going to merge it by doing alpha times WRB. Let's call WRB B and WRC C. So it's going to do alpha times B plus beta times C. That the verifier will get this. So this will be like the merged claim sum. Understand? From those two claim sums, it's going to use this one to merge it. So now the prover will create an FBC polynomial that also has alpha and beta in it, and try to prove that it's equal to the merged claim sum. Let's call this guy, let's say CSM, merged claim sum. So he wants to create an FBC polynomial that is also merged. Now to do that, it's almost like doing the same process that the verifier did. So it's going to calculate alpha times add I, then this one times, is it times or plus one? Sorry, add I times WB plus WC plus beta will come into times mol I the whole mol this thing. Right. This is how the prover will also calculate the merged ABC polynomial. So using normal number manipulations and all, we could multiply add you can have add times alpha.
I just use
No, look, I just think like I'm like what should you put on down then let me go back to the article. I can switch it from here. I need to already. It doesn't to be changed. So using the article here, let's just follow this one. So the prover is sending B is W evaluated at RB. Can you see it? Can you? We are squinting your eyes like that. Is it better? Guys from the back, Mitch, Joshua, can you guys see it? Okay. So the prover sends W evaluated at RB, that's our B, and W evaluated at RC, which is our C, big B and big C. They're just new names. So we won't just keep repeating W and WRC. So now to merge them, the verifier does this to merge those two guys. It does alpha times B, which is our WRB, plus beta times C, which is the WRC. Right. So it's going to so this is like the whole thing was calculating here. Now if we're to like compute to create the what's it called again, the FBC polynomial, that's the prover now, you could like expand on this is how the equation would look like. So it's going to be alpha times RDI out there then the RBC. So this is going back to, you know, when I said R0, R1, R2, that our RDI is evaluated at 3 points. So this that stuff here again. RB, BC, those are the two new guys. That's BC, like the two new random challenges. So this RB is like the random challenge from like the previous, the main one. But when we get to the permutation, we understand that. So plus W evaluated at B, which is the current random challenge we're working with, and W evaluated at C. So plus alpha again. Okay, yeah, that's true. You're correct. Alpha evaluated at multiplied by this guy plus beta times this one and beta times this one. So then we could sum it up into this one here and then still reduce it somehow into this. Like this will be the new add. Like if we were to pick the adds from these two places. No, W, this like, should I say factorize? Are we factorizing here? Something like that. So W, B and WC are the same in both places. So we could just bring out these two guys and compute them separately, but use the same summed and multiplied W police. Are you? So this is like the algorithm now to calculate that. So we first get our B and C from the prover, and then we do our add partially evaluated at the RB, the B and C, and then our moduli evaluated at RC and RB, So we evaluate both RDI and MOLA, both RB and RC. Remember, those were the random challenges that we used to get our B and C. In case anybody wondering where RB and RC came from, that's what we evaluated W at to get B and C. This RB, this one, and this RC.
Those are the
Previous subject.
Yeah, sort of.
Sort of,
Yeah, that's it. Like
is it
it is.
And when so we should go from there, of course,
I just said sort of like you also say it that way.
see that way, that is the way.
It is. It is. I mean, like there are many ways you can say it.
How what should I find see that is that more than
And the previous one.
yes, some previous one.
Yeah,
There's
previous
more than
subject.
this.
Yeah, the same thing.
Oh my God.
The same thing. So and then B and C are the new ones in the current round. Those are the new random challenges in the current round. Yeah. So we are going to evaluate RDI at both RB, new B and C, and then we also evaluate add I again at RC, then the new B and the new C. This is different from the big B and the big C. This big B and this big C. So our big B and the big C are W evaluated at the previous RB and the previous RC. Good. So after we do that, we scale with alpha and beta, and then we sum two of them up to get like the new add and the new moduli that
So
we'll be
this is
using.
still the proof,
Yeah, this is the proof I'm trying to get the ABC polynomial. So our ABC polynomial will now look like this. It will be the new RDI. Remember, our new RDI is the two RDIs scaled with alpha and beta sum together times WB and WC plus, in this case, that's W new B and W new C. Since when you get to implementation here, those things can get confusing, sort of like, is this the old, the new? Me, I struggled with it. So, and then it's going to be plus the new moduli. It's all the same structure, but we've already changed the RDI and the moduli in a way. And is it making sense? Like this part is quite.
this part can be really confusing. It is. Again. So this part is confusing, and the thing is that we have two sum checks, right? And we have two sum checks. I'm trying to reduce it to one. So if you scroll up, to W, yeah.
I think I've gone back this.
Okay, so here, these are W evaluated at RB is equal to B. This B is constant. It's a number, right? And this still the same W evaluated at RC will give C, right? So we can think of these two things, this one and this one. We can think of it as a new sum check problem. Two different sum check problems, right? But we don't want to do two sum checks. We want to merge it to one. So we want to merge those two sum checks to one. And how do we do it? We multiply them by, we multiply WB, or we multiply B by alpha, right? And we add it to beta times C, right? So
is my screen.
Oh, that's it. Okay, so
I'll scroll the red. Okay, I'm not even connected. Let me on hotspot.
that's all.
Yeah.
Oh, my network. Yeah.
Yeah, because they see
I think I'm going to this first.
Yeah,
Yeah, should be joining back then. Okay, I'm back. That's what it is explained.
So, okay, so this B and this C are basically evaluations of WI at RB and RC, right? But we want to merge the both of them, like these two. We want to merge the both of them. And in order to merge the both of them, this is basically the same thing as doing alpha times W evaluated at RB plus beta times W evaluated at RC. We know that when we evaluate W at RB, we get B, right? And when we evaluate W at RC, we get C. Normally, we would have had to prove this W evaluated at RB using a different sum check and W evaluated at RC using a different sum check. So those are two different sum checks, right? But we don't want to do that. That's why we actually do this merging, in order to get one sum check that we can use to actually verify that this holds, right? So we are now going to perform a sum check on this, like WB, WRB and WRC. But we need to merge them so that we'll have one sum check. And what is sum check basically? We're trying to prove that the sum of a polynomial over the Boolean hypercube is equal to a particular value. So what are we trying to prove? That the sum over a polynomial, which is f of RBBC, over the Boolean hypercube will give us WB, WRB, and the sum over a polynomial over the Boolean hypercube, which is f of RCBC, will give us WRC, right? So if you scroll, so this is basically it, right? So this WRB, this is the f of RBBC. We know what f of ABC is, right? It's add I RB or add I ABC times WB plus WC plus molli ABC times WB, right? Times WC. That's normally what the sum check equation would be, right? But because we are multiplying by alpha, that's why we now have like alpha times add I, right, plus alpha times molI. This is RB. This is also RB, right? So we're using alpha to multiply through, right? And that's how we get this alpha times WRB. Does that make sense? Makes sense, right? So, yeah, that's for the RB. We use alpha to multiply WRB, which is basically using alpha to multiply FRBBC, where we know that FRBBC is RDI evaluated at RBC times W evaluated at B plus W evaluated at C, and molI evaluated at RBC times W evaluated at B times W evaluated at C. So next we need to now look at WRC, right? And it was beta that we were using to multiply WRC, right? So that's basically why we have this. You know, here we have already done the multiplication through, right? But if we wanted to factor out, we'll basically bring out this B and then have these other guys, right? So when we multiply by beta, that's when we have beta here and beta here too, right? Okay, so the idea is that we want to add this guy alpha times WRB plus beta times WRC, right? And we can already see what the expansion is, right? So when we sum the both of them, this is what we get: alpha RDI RBC plus beta RCBC. You know, when we see beta is RC, when we see alpha is RB, right? So we have this, and then times WB plus WC, right? Plus alpha times, this is for the mole now, this was for the add, right? For the add, when we see alpha, we have RB. When we see beta, we have RC, right? And then this is the W part, WI plus 1 BC. So this is the add I part, right? Makes sense? Does it make sense?
Yeah.
Sure. Billy Kiss, favor. Peter. Yeah, the complete. Although I'm not finished. We're done with the add part, right? Let's look at the more parts now. Right. We have alpha molI RB. You know, when we see alpha RB, right? When we see alpha RB, when we see beta RC, right? So we have alpha times molI RBC plus beta times molI RCBC. Then we multiply it with this WB and WC. So we can see that WB and WC are not really affected. What is majorly affected is kind of like the add and the more. So we can just take this. Is it that? Okay, sorry, this. Right. So we can take this. Okay, we can take this as the new add-I. All these parts here. We can take it as the new add-I, and we can take these other parts as the new molI. So what is the new add-I? Basically, we have seen it here, but let's just outline it so that it will be clear, right? So Okay, okay, good.
Wait, this line is lagging now.
It's lagging.
It's
It's
network.
lagging.
I'll scroll down everything.
That'll be my network.
No, it's not. Is it? I don't know where it's coming from.
The line looks fine.
Yeah, we use the.
Okay. So what is the new ADI? We have the old ADI, right? We have the old ADI, and then we partially evaluate it at RB, right? And after partially evaluating it at RB, the size of the array is going to reduce, right? Then we multiply it by a scalar. What does multiplying by a scalar mean? We're just scaling every element in it, in the evaluation array, right? We're just scaling every element by alpha. And then we have plus beta, ADI, but now we're partially evaluating at RC. Right? So when we partially evaluate at RC, we get a new polynomial. Then we multiply it by beta. Right? So this is going to be our new ADI. So after we've done this, we are going to get a new ADI with respect to BC. Because after we do this, we get an array. We do this, we get an array. Right?
The call was about to begin.
Serious.
15 minutes.
So after we do this, we get an array with respect to BC, right? Because we have concrete values for RB now, right? So we get a new polynomial with respect to BC. After we do this, we get a new polynomial with respect to BC. And you know we can always add two polynomials that have the same. So we just do 11 twice and we get a new ADI polynomial, right? The same thing for the mole. The mole line we partially evaluate it at RB to get a new mole RB, right? Then we multiply it by alpha, right? And we also do the same thing for RC. The mole line we partially evaluate it at RC, right? We get a new polynomial with respect to BC, multiply it by beta. Then these two polynomials now with respect to BC, with respect to BC, we can now add them element-wise to get the new mole. So at the end of this, we are going to have a new ADI, which is just an array of evaluations with respect to BC, and a new mole, which is just an array of evaluations with respect to BC. So with that, we can then construct back our FBC using the new ADI and the new mole and the WB and WC. I don't know if it makes sense. Like, there's a lot of variables flying around, right?
Sorry, yes.
Just to okay. Is it that you use this particular 213 when you use the next day? Like
Okay.
a 0 from the top.
You know, like after you verify layer 0,
Yeah.
yeah, and you go to layer 1, the sum check of this thing of that layer 0 will give you random challenges, right? So that random challenge, if you split it into two, you're going to get RB and RC, right? So once you get that RB and RC, that means you now have two new sum checks to do. That's when you now actually need to fold. Another chapter.
Yes. We talk about check at every layer, right? Now, if you say that you are going to now, you know that if you are using the FPC, there was going to be another parameter
There'll be a W inside that FBC
So how I know to them like FC layer?
at every.
Layer, because
Is it for the prover or the verifier?
for the verifier to check that the alpha W RB plus alpha beta W also equal to the FBC alpha plus the FBC beta which is the polynomial for the next layer. It's also like equal. I'm saying that like you know that new polynomial has W's which is like subsequently like the W of the next. This is subsequently the FBC of the next.
Of the next layer?
Now, how are you going to evaluate? Because I was asking, so what I mean is that you only get to evaluate at first check. You have to check at the last layer. How are you going to do the check at every?
Do those checks at every layer since the verifier doesn't know WB and WC, right?
Yes.
Is it?
Okay, you talk about the verifier sending the W.
No, the prover.
So before sending W to the, so before we say so W of let's say of this that left hand side, then W of the next one, and now use that to evaluate the to input it to your FBC. Then you to now check. So that means that the verifier can only do the check after the prover evaluates the next FBC.
I don't know if I got
Get
clear.
that, Abi?
I said the verifier can only do the check.
So it said that the prover sends WBC BC to the
To the
verifier.
verifier.
Now
Sends WB and
W sorry
Send
different
both of them.
yeah. So all I'm saying is that so that we are checking W alpha W alpha and alpha beta W alpha C. We are checking it against the FBC of the next
of the next
layer.
layer.
And I was not saying that the FBC has its own new W, right? So now what you're going to do is that you would now evaluate with the W of the next layer.
Okay.
So I'm
Yeah.
asking like from
Yeah.
the next layer, you need to choose that FBC to like get a constant that you're going to compare with the alpha beta of this that one with the previous.
That is of the previous layer.
Yes, so that means that you're because the way it makes sense to you that you are doing it subsequently so that you can do the final last oracle check.
Oracle check. You know, it's just like sum check,
Yes.
right? In sum check, you have
The round checks.
yeah, so you have the claimed sum,
Yes.
which was gotten from the previous layer, right? And then you're now trying to prove that that claimed sum that was gotten from the previous layer is actually the sum of the polynomial over the Boolean vacuum of this current round. So if I think of it that same way, yes, where that left hand side is the one that was gotten from the previous round, right? Which is that which is that alpha times b plus beta times c, right? You can think of that as the claimed sum which was gotten from the previous round. You get it? And then for the other parts, now for the right hand side, that's where we now do the sum check,
Yes.
right? So when you do that sum check, you're now going to get new RB and
Yes.
RC.
Yes.
You get it? But the thing now about that one is that the prover, the verifier does not know WB and WC, but the prover sends
It's
it to him.
okay. Then now input it into that. Input it with this other alpha new add. This with the add a new add and new more.
Yeah,
Then it does the
and
multiplication
does
for the
multiplication.
new add. Then sorry addition for new add and for new more. Then it gets the same polynomial but in evaluation.
For an evaluation, yes, evaluation. Because now these ones will now be, these ones have been fixed already by the previous round.
Yes.
Then these ones will now be gotten from sum check,
Current layer.
the current layer sum check, the random challenges, right? and then the prover is going to be the one that will send the W I plus 1 evaluated at B and W I plus 1 evaluated at C, those concrete values, so that the verifier can do the check.
Yeah.
Makes sense, right? Okay, strike out. Oh. No, you can still cut. You can still you know, like there's something about explanation, right? Like 5 people can explain the same thing differently. And in as much as you hear all those explanations, those people were explaining it differently, but they were saying the same thing. And if you're able to hear everybody's explanation and know that they are talking about the same thing, then you truly understand that thing. Let me not say truly understand, but to a great extent, you understand that thing, right? So everybody's contribution is always very important. You don't know, like 5 people may be explaining the same thing, but it doesn't click for somebody, and then one person just explains and it clicks, right?
Okay, so what Francis was basically saying is that, you know, what we are actually trying to prove in GKR is that every layer is linked to the previous layer, right? So now, if you know the first process of when you want to start doing your GKR, when you have output, the first thing you do is like, the output is like, you have the output polynomial, right? So normally you like commit the output polynomial and you generate a random challenge. So when you generate that random challenge and use it to evaluate that output polynomial, it gives you like a claim sum, right? And what you're trying to prove is that you're trying to prove that that claim sum result is also related to the layer below that output layer. And the layer below that output layer, the W polynomial at that output layer is equal to that FBC of the layer below. So now if you compute your FBC correctly and you evaluate it correctly, the value it will give you should be the same thing with the value, the claim sum of the output layer. So similarly, whatever the claim sum of the layer below the layer 1 gives you should also be the same with what the layer under will give you. So that is just the hierarchy of relationship they are trying to prove. So that is
Okay, so, well, I hope this makes sense. Like, this will probably be, okay, it's not even this. I wanted to say a lot of people will get stuck here, but it seems where a lot of people are getting stuck is in the sum pool. From the look of things, like, that seems to be where a lot of people are having issues.
Sorry, what do you some poly?
Like,
The FBC poly.
yeah, FBC pool. Is it? Yeah, the FBC.
Okay, you check full school, Abi. That one you concluded that probably.
No, I'm just
Creating the FBC or
creating
that
the
some code structure.
creating the FBC. Have you created the FBC?
I just resolved it, sir.
Okay, you've resolved. Have you created the FBC? So this is basically going to be the next
FBC.
let's say difficult thing. So if you have this figured out, then the next thing will just be putting everything together to create a protocol. Right. So how many people have this already? You've not
I'm not done this.
the 2 to 1 2. Have you done the 2 to 1? So I think that will be like the next major thing for you guys.
Right, that she was explaining. Oh, that's what I was explaining already. So
Yeah.
just continue to it. I mean,
That's it. So,
yeah.
so the way I'm seeing it, we may still do like tomorrow.
What's if only this one joins? But I'll put my GitHub here.
Okay.
So the limit to apply. Anyway.
Is it? I mean, it's this one so that you can still do
Yeah, and two of them, they're the same account. So
Yeah,
it only happens when two different
Different
accounts.
accounts.
Yes, so it goes memory. That's why it's not doing 1 hour limit.
Okay. Okay, so you open your GitHub.
Yeah, just GitHub there. OBE. Then we try to replace.
So it seems tomorrow another person is still going to do the person's code review. Right. So let's use today and tomorrow for code review. So after today's code review, go back, you look at your code, right? Implement. Then if you have any challenge, when we come back tomorrow for the second code review, everything should, I'm hoping everything should make sense by that tomorrow. Is that okay?
Yeah.
That's fine, right? So basically, we're just picking different people's brain, right? To see how they went about their
Process. That
implementation.
call has ended.
Hmm?
That call has ended.
Okay.
So she just like
Can you see this going on?
Is this okay? Yeah, yeah.
Like the brightness.
Yeah.
Still saying this guy. Oh yeah, yeah, out is there.
I can refresh the link. Obvious can
Let me just see this. Let's see the
I get this free What's the breakup now? I didn't even give you
Don't worry. Don't worry. Don't worry.
That's fine. That's not too sure. This is not so. Right. So this, it's not position here, guys.
February 2013. Yes. I read like 3 paragraphs. I'm scared. Field trips.
I've seen Nigeria.
So if I choose this one,
How did you switch it? How did you switch it?
Yes.
like
Yeah.
What's it?
Like, what would I call it now? I don't know exactly what you use. So maybe like an ambassador and stuff.
Okay.
Yeah, I'm doing
Can you guys see it?
I think you zoom in, you say, can you guys see it?
I don't know now.
Ah, sorry, sir. I'm here because I like
It's not clear, right?
Let me see.
What about now? Can anybody see? Frankie, is it clear from there? You can see from there. Okay. So yeah, we are looking at how to create the APC polymer, the one that has alpha and beta in it. The implementation, how to implement it.
As in the new
Yes,
APC.
the new APC.
I'm comfortable with the way it's I think there's a way they can use VS Code and code space. Yeah, code space.
I
I
think
forgot
it's control
the
dots.
control dots.
Dots.
Yes, I think it should be control.
Yes, it's very
When you know that bigger, please scroll up and down.
So it's
see it.
Yeah, click on the drop down beside the pencil. Yeah, git up there.
I mean, I don't like the web interface.
Oh.
Why do you switch? Why do you switch?
Yeah, to move between, you know, the control click to move to a function.
It was like, why did I leave VS Code? Okay, so that two of us could not be on the course. It was
For
ending
a long-
everyone 1 hour. So, only
It has verified
yours.
OBS. Is it okay, right?
Yeah.
You may need to zoom in again. Is this okay? Size.
Yeah. No.
Everybody can see, right? Okay. So we're looking at how to get the FBC polynomial, the one that has alpha and beta in it. That's one merging, doing that new addi and new moduli thing together. So this one, it takes in the layer, that's the current layer we're working on, and then the WB and the WC. RB and RC should be the old RB and the RC. I can't remember. Yeah, it should be the old one. Yeah, from the one from the sum check, like the previous layer. Then the alpha and beta too is the one example alpha and beta. So as usual, we first get the add and the normal ones. Then so you guys remember we had like two addis, like one with beta and one with alpha. Where the one with alpha had RB, the one with beta had RC. That we added together to make our new addi, right? So this is it here basically. So I think the addi itself, I have a multi-partial evaluate function in my RB, in my multilinear polynomial. So the reason why this one is there is the RB and RC at this point, they can be multiple values that are going to be vectors at this point, and the deeper we go in the circuit, the more it increases. So we need to like partially evaluate at all those points. So that's just what this multi-partial evaluate is doing basically. So Alright guys, so yeah, this is just basically partial evaluating the whole polynomial, but on the same point sort of. And then scale with alpha. So that scale is also a new function added to my multilinear polynomial. It multiplies each value in the array with alpha. Same thing with scale by beta. Multiplies the addi divided as RC with beta. So then you adding two of them together. The add RB alpha times add RB plus alpha times add RC gives us our new addi. That's why I call this summed addi. I could have named it better, but sure. You guys get what is happening here? Huh? Mitch? Just smart dev. Phil, you get what's happening there? Levi, sorry. Jerry. My boss.
The RB
Okay.
is from your right.
Some check. That was for the previous round. I'll be from the previous one. So let me just show how I'm bringing it in.
Wait, sorry. Before you go there, let me just say something. Like, there's something about code readability, right? And when people were implementing your sum check, I said your sum check protocol should be 3 lines of code, right? There was a reason why I said that. Like, not the entire protocol, but like, say your sum check test, you should have a polynomial. You pass it to the prover returns a proof. You pass it to the verifier accepts or rejects. That sounds like English, right?
Yep.
And like, I just wanted to relate it to this. We saw how the explanation was, right? We said when you have RB, like alpha times add I evaluated at RB, right? you see how it sounds like English, right? We have alpha times RDI evaluated at RB. We have beta times RDI evaluated at RC, right? So you see how it just sounds like English. So when implementing, it's usually good to like factor all these things. Your first implementation, it may not necessarily be like this because you're still trying to get the protocol to work, right? But like after everything, just try to see that when you're reading through your code, it's basically as if you're reading a book. Like it will make things easy for you to understand.
Okay, so I wanted to show where RB and RC were coming from. So exactly, thank you for this is where current RB and current RC, which was me keeping track of. It's not actually it's not an array that I'm pushing in values into. It's just because it is an array itself. Like I'm not storing them in an array. They are arrays by themselves. I don't even know if that makes sense. I'm replacing the old array every time. That's why it's a vec new. It's not that I'm pushing them into here. So in creating our new add we use the previous random challenge in creating our new one. So that's why I'm like keeping track of it out here outside the loop. So when this is done, it would update it. It will update it with the current one that okay, this current one will be the new old one for the next round. Here you get. So it is coming from the previous. That's random challenge for the previous round. So is it making sense, MJ? What's the A there? What part? So, wait. At this point, we have like different random challenges. We have one from the previous round, and we have another set in the current layer. Sorry, not round, layer. Is in the subject that round. So we have one from the previous layer, and then we have one in the current layer we're working on. So we use the ones from the previous layer in evaluating our add. Our add is meant to be evaluated at A already. So that A is the previous random challenge. The RC is for the ones with for the second side, the ones with beta. The ones with alpha is the RB this thing. So I'm just keeping track of it here and then I'm passing it into this place to get my mesh ABC polymer. The mesh ABC polymer is just the one that has you say ABC polymer, but it's the one that has alpha and beta. So is it clear now? Okay. So let us go back there. So we first do our new adders and our new molars, and then the polynomials. So this from here onward, it's now the same thing as a normal ABC polynomial. Just sum your W polys, multiply your W polys, put them in your product poly, put it in your sum poly, and return. This is what is different between two of them. The way the adders are computed. The adder here does not. The adder here is just partially evaluated as the random challenge. So for this one, so I could have used that multiple partial variable. I know that at this point there will always be just one. It won't be multiple values. It will only be one random challenge. That's why I'm just doing one partial evaluate. But that's like implementation choice, yeah. So you can do it. So let's not go to that.
Well, I'm against.
Yeah, I guess me separating them.
No, like even your output for the learning can be more than one bit. Right? It's just because of this, like
Okay.
the way you're going about it. But it's possible you have a circuit that has more than one output. Yes. So for that one, like
There'll be
Good.
multiple.
Yes, R0 will not just be one random challenge, it can be multiple.
Okay.
But like that one is just implementation.
I will change that. So that's just what is different. Basically, we taking beta and alpha into account in our ADA and online. So is it clear to everyone? Any question? No. Okay. So let us go back. Let us continue the process. So after we get our FBC polynomials, and on either layer, we now want to perform some check on. We want to perform some check. We are trying to prove that our FBC polynomial is equal to a claim sum. Either the claim sum of this layer or for the next layer, for whatever layer I want to prove that the FBC polynomial, which
Sorry.
yeah.
What you were saying just now about if we had more than one output, would that mean that we have to be applying alpha beta
Every time.
2 to 1 tree from the beginning?
No, not necessarily. Because that output polynomial, we are still going to evaluate it at a random challenge to get the claimed sum. Right.
Yeah.
So there's no need. But if you want to, I understand why you asked the question, right? Because of how you guys implemented.
Yeah.
Yeah.
Actually, I was thinking our own was fine because in that particular scenario we need to apply alpha beta at the beginning. But you have you have more than one R.
Yeah, you have more than one R.
And yeah, that's what you said before. So if you have more than one R, that means your A will be more than one.
Your
A will be more than one.
Yeah.
your A, yes, your A will be more
Your
than
A will be
one.
more than one.
So that's what was against. I was using partial evaluate for just one value.
Okay.
So it's actually
Well,
still made it multiple.
But the thing is that when that your W0 polynomial, when you sample R, right? R may be 2, maybe 3. But when you now evaluate, because it's a full evaluation,
Yes,
it will give you one value,
yes,
which is the claimed sum.
okay. Yeah, that's true.
So I think
With my system.
Okay, sorry.
okay. So I think that multi-party you use can still work
Yeah, sure.
in the sense that now your arrows, instead of passing the value, just pass it as an array of that value.
So you still do one
you
and
still
then
do it at the same time.
it still works for one.
Because with this now, I'm also seeing a problem with my implementation, because we are checking if the length of W0 is equal to 1. If it's equal to 1, we are now padding, right? And when we pad, we now handle it like, when we are handling that W0, we are now if the layer in that loop is equal to 0, then it does the partial evaluate with one value. You understand? And we have already checked out if the length is equal to 1. Now, what if in a case where the length is not equal to 1 and we don't pad? We now enter and we still use that. If the layer is 0, we are still passing 1. That's what it's basically saying. You understand? So that check we are doing there are some times where the output will not be 1, which means it will still handle with this thing. And if the output is not 1, which means the randomness will be more than 1. And we are using the layer count from 0 to handle the partial evaluate. So it's going to fail at that point for a case where the output is not 1.
That's
How do we fix this and that?
Wait, I don't get what you mean when the number of points.
So in our layer loop,
GKR.
in our layer loop,
Yeah.
we are looking from 0.
Yeah.
Now, inside that layer loop, I'm talking about my implementation now
Okay.
and what is showing here. Inside that layer loop, we are now checking if the index is equal to 0, the way it's going to handle the other ABC is different from if the index is not 0. Which means the way it's going to handle the other ABC, it will just partial evaluate other ABC at 1, right? But others is going to partial evaluate them at the randomness. Now, and you know, at the beginning when we are computing our layer 0, we are checking if the length of the output is 1. If the length of the output is 1, we part with 1 with 0, right? Now, which means there are cases where the length of the output will not be 1.
Sure.
And in that case, when the length of the output is not 1, the length of the output will be like 2 or 3 or 4. Sorry, will be like 4. You understand? It's still going to come inside that layer loop. And if it comes inside that layer loop, still that output is still layers, is still at index 0 in that layer loop. And there we are partial evaluating at 1 value.
Yes. So I asked this question to Wisdom.
Yeah.
And Wisdom was like that in that first layer, that's the output layer, you're only getting one interested value. So you are always going to like pass in that, always commit that first layer output to the transcript to give you just one value. So you are always getting like for the output, because you've passed in your set of inputs, the verifier is giving you a set of inputs and you are getting one output. So always when you commit the initial polynomial, that's the output polynomial to the transcript, you are always getting one untrusted value from that transcript. So it's when you now perform some check that you are now getting multiple untrusted values.
Okay, so the thing is, you know, your output mustn't always be 1 value.
Yes.
So your output is like,
regardless, even if you have 7, 8, like no matter the amount, like you are always just going to commit that output polynomial because that's where you are starting from. So you are going to just commit that as like this is evaluation points to the transcript, and you are always going to get one value. So you don't need to bother about.
I think, but I don't know if there's something I wanted to say. I don't know if it addresses this. I think, like even for that output layer, you should probably have a get number of variables.
Yes.
Right.
Actually, true.
Yes.
Like the
So
number of
that's
R's,
solved.
basically, that was solved.
That was solved.
Yes.
So once you get the number of variables, you use that to sample the challenges.
So you're saying like based on the outputs, like the evaluation points, you obviously know how many points to fully evaluate that polynomial at. So that you just generate the number of, based on the output polynomial, you generate the number of R's to evaluate that polynomial, but everything is trusted.
but if the output layer will have number of arrows that is not just 1, like it has more than 1 number of arrows, which means that check we are doing inside our layer loop will have issues.
No, like the number of R's that you're generating now is actually for ABC to get
we
just one claim sum.
So that means for the output layer, the number of bits, you know, R is basically what we are basically saying is when you get your random challenge.
Sorry, I'll not say ABC, right? I'll say R1, R2, R2.
So,
yeah, but it's the same thing.
So what I'm saying basically is, so that means the number of the bits of the output layer, you're saying it will always be 1. No. If the bits is not always 1, then evaluating inside that do that check if index is equal to 0 and evaluating at just 1 arrow, at just like 1 arrow, not you know the vector of arrow.
Yeah,
it's going to fail.
You know you put that check to get number of variables outside. You still do that check inside.
So that means our current implementation now will not work for that. That's what I'm saying.
When you want to evaluate the review, you want to check. With the verifier now, you want to check the claim sum with the evaluation of FDS. Right? It's possible that your first polynomial might not have 1 random value, might have 3, But in our current, we always assume that the first one
I'm not
was
assuming.
one.
Wait,
Ah,
wait,
yeah.
guys.
You are not assuming.
Wait, please. We should,
Oh, sorry, sorry.
like, after the class, we can just go over it. So it's like over a lot of things. So, back to where we figure it out, sha, if it is one or how we handle that case. But so far, where we are for everyone else, is there any question? So far, is there any question
So
from?
that's why, sorry. So that's why like this session so having is important, right?
Yeah, I have a question. That time, why do we apply AFAN? Maybe it's we apply it. Okay, let's say the first layer now. The first layer we did our FABC, whatever, we did something, then we got to random challenges. Then the second layer, it has two evaluation points. Right?
So untrusted.
There are two untrusted values. So those two untrusted values, we're supposed to put. What are we supposed to do normally? Let's say we don't do AFAN. What are we supposed to do?
Normally you will do two sum checks.
Two sum checks.
Yes.
If I want to
You do one sum check for WRBC, where WRBC is the claim sum. Right?
okay.
Then you generate a new ABC polynomial to prove that WRBC is the claim sum.
Yeah.
And then you do another sum check for RC.
Guys,
What did I say?
you said the BRBC at first.
Sorry. So for WRB, right?
Okay.
So then you do another sum check for WRC. Like a different sum check with its own F, which is own FRCBC.
So it will be like they are separate.
Separate.
Normally it's like 4 polynomials. So separate. It's like 4 evaluation points. So separate it. So this one will have 2. This one will have 2. Then we'll do WRB here. Then WRC.
RC, yeah.
And
That's two different sum checks.
2 different sum checks.
And then those two different sum checks,
It generates like
they will generate their own 2 again. You will now be doing sum checks for
Keep
4.
blowing up.
So the deeper the circuit,
so it's by
yeah, 2 raised to the power n sum checks basically.
So that means some check was supposed to be running. Some check was supposed to be running based on the number of. Some check was supposed to be running based on the number of gates in a layer.
yeah.
That's how that's how it was supposed to be running. But because of the 2 to 1, we are now merging. Like if there are 2 gates in a layer, it's going to run the sum check on the both of them at once. If there are 4 gates in the layer, it's going to run sum check on the 4 of them at once.
Like thinking about it that way is kind of, let's say, like that 4, there will be no need for the 4 again, right?
Because the folded soup that we had just gave you 2.
Yeah, just give you,
Soup down now.
yes.
It's like one.
Or
always
let's say
do
the
that.
folded soup. When you folded the 2, you got 1. So that 1 now give you 2 again.
So they are folding the 2.
So you're folding the 2
So you
again.
become one.
So you get 1. So like normally it would have been 2 and 4, right?
So that what I'm saying is normally if we weren't doing the folding, there have been some check 2
Yeah.
on the layer that has 2 gates, right?
Not necessarily 2 gates, right?
Like
Like even if it was, let's say, 50 gates, the thing is we're picking, you can think of it as we are picking just one gate that has two inputs. So it's the inputs, not necessarily the number of
Okay,
gates.
so that I don't maybe I'm calling it and it's confusing.
Okay.
What we are basically running subject, if we're doing the folding of, you know, every gate has two
Two
inputs, right? So what we are running some check on is the gate and the input, like
Yes.
because that's the gate now, two inputs, the operator and it gives you an output. So in something like let's say a layer that has two gates, which means we run some check on the input and the output, and we run some check on this one and the output. So that would have been two sum checks in that layer. But because of this folding now, we merge everything as one and run some check on it. On a layer now that has 4 gates, which means there will be 2 inputs here, 1, 2 inputs, 2 inputs, like that. So on a normal, if we're doing folding, we would have run some check on each of them individually.
Like the way you're, I know you're seeing it as the input, but I don't know. Maybe
So
that's
I'm
a
not
question
talking
now.
about the folding. I'm talking about normally without the folding.
Without folding.
How were we supposed to run some check on the circuit?
So normally without the folding,
Yeah.
you know, even if layer 0 had, sorry, let's switch. Okay. So even if layer 0 had, let's say, 2 gates, right? When we partially evaluate this guy and get 1, this one, which is our claimed sum, right? We know that there are 2 things that will actually feed into whatsoever gate it is to give us that claimed sum, right? So this is like 2 different untrusted values now. This one and this one. So even if this other layer had, like, let's say another 8 gates, it's not on the 8 gates per se, right? It's on this one particularly.
Which one?
This.
I don't understand.
Right. Like the way you ask the question, I'm seeing it that you're talking about these gates.
Okay, so what I'm trying to understand is without the
Without
folding,
2 1.
how were we supposed to evaluate this stuff now? Like how were we supposed to run some check on this?
On
So
this.
that if we know how we're supposed to run some check on this, we now relate it to what the folding is actually solving.
Okay. So if we're not doing the folding, I'm just going to take it that one of, or the random challenge is basically maybe either 0 or 1, right? But now the random challenge will be outside the domain, which will give us a point, let's say here 50, right?
When you say normally,
Okay, like these are W polynomial.
yes.
At 0, we get this value. At 1, we get this value, right? But when we pick a random challenge for W0, we are moving from this 0 and 1 to a random point, right? And now this random point there must be input values from the layer beneath
Yeah.
that gives us this as the claimed sum, right? So normally we are now meant to perform some check on this guy and some check on this guy.
So, on using this guy now,
Okay, this guy.
yeah, the one on the circle the stops we are going to perform some check on as like.
Okay, so if our random challenge was 0, we are going to perform some check on. Let me reverse this. We are going to perform some check on this and on this, right?
Okay.
Two different sum checks, one for this and one for this.
What about the one on the right?
No, we're not going to perform some check for this here.
Why?
It's because the value the prover gave us was the evaluation of the polynomial at this point. Let's say it was 3, and the evaluation at this point, let's say it was 4, and let's say this gate was an add gate. So this was 7.
Okay. So now we are performing two sum check here at the point of 3 and the point of 4. Right?
At the point of 4, yes.
Now, so that means if the claim sum is 1, we perform on point of 5 and point of 6.
Yeah, if the claim sum, or if the random challenge was 1, we are going to perform some check on, let's say this was a multiplication. And let's say this was 2 and this was 3 and this was 6. Right?
Yes.
We are going to perform some check on this guy, which will say, let's perform some check, let's prove 2 and prove 3.
Okay. Now, how many sum checks are we performing? 3, 4, 5, and 6. That is 4 sum checks.
No.
That's
See,
what I'm
and
saying.
See, we are doing only one, we are not doing for all of them.
I don't understand.
This was what? 4, right?
Yes.
This was 3.
Uh-huh.
When the verifier picks a random challenge, say that random challenge was 0, we are talking of this,
Yes.
of this guy,
Yeah.
right?
Yes.
We need to perform some check to prove that this guy is actually 7, right? And in order to prove that this guy is 7, we need something from the layer beneath,
Below, yes.
which is 4
And 3.
and 3.
Okay.
But the verifier does not know 4 and 3. It was the prover that told the verifier 4 and 3,
Yes.
right? So the prover also needs to prove that 4 was gotten from this layer and that 3 was gotten from this layer. You get? So the prover will now need to do another sum check to prove 4, where 4 is our WRB and our WRC is 3.
So, are we neglecting?
We are
One
neglecting
on-
it.
So we are not running some check on that one.
Why? I mean, the
Because-
security is not complete.
No, the security is complete because we did this randomness. We use a random value to get this point.
Okay, so now, so if our output is 2 values, like two points, right?
Yes. If our output is 2 points,
Yeah.
we are going to have that W polynomial, right?
Yes.
And we can evaluate it at a random point,
Yes.
which is this point,
Okay.
right? And what we are basically trying to say is that there must be 2 inputs
Yeah.
from the layer beneath
Mhm.
that will give us this random value.
Okay. Okay. So it mustn't be all the layer, just any two from the guys below.
Yes.
Okay, okay.
So it's some check that would give us those particular two, which will give us like the RB, right? And the RC.
Okay, so now, assuming this is how it will work without the folding, right?
Yeah.
Now, the folding, what will the folding do now to
Wait,
this?
can I just take this one step lower?
Alright, yeah.
So that, like, now we have 4 and 3, right? This 4 is an untrusted answer. It was given to us by the prover.
Yeah.
3, so it's untrusted. It was given to us by the prover. So we need to prove it. And in order to prove it, we need to prove that it was gotten from the layer below it. We need to prove that it was gotten from the layer below it. So let's say this was an add gate. Let's say this was an add gate and this was 2, 2. Right? And let's say, what can I give us? 2 and 1. Let's say this was an add gate 2. 2 and 1. Right? So we need to prove that 4 was gotten from the layer below it. And in order to prove that 4 was gotten from the layer below it, we are going to do some check. Right? And while our RB, like when we do some check, W at this layer, evaluated at RB will give us 2. Evaluated at RC will give us 2. That is 4 for this guy. Right? Because you know we're meant to get an FBC for this guy and an FBC for this guy. 2 different sum checks. Is it making sense?
I think so. This is what I'm trying to get. I want to get like the point where, so that it will make the whole folding make sense. So we want to get the point where, let's draw a complete circuit, like a complete circuit up to the output. Then we mark the point where some checks are being done without the folding, right? So that we understand the number of sum checks that will be done normally if there's no folding. Then we now see, okay, when folding is done, this is how the sum check is going to operate.
Okay, let's do that. What should be our input? Eight, right? It's 15, right? It's 50, right? This circuit is okay, right?
Yeah.
Okay. So, you know, or should we leave the 50 so that our output gate to be 2 values?
We can leave it like that. We can take it like this downward.
We can take it like this.
Yeah.
Okay. So, Some check. First thing first. If we're looking at this as our W0, this is our W0, 50 is our W0 evaluated as 0. What it basically means is W0 is always a univariate polynomial, right?
Yeah.
What it basically means is that W0 evaluated at 1 is 0, right? And this gives us a polynomial in one variable.
Yeah.
We evaluate this polynomial at a random point.
Yes.
If it was 2, or if it was 4, it would have been a polynomial in 2 variables, right? And we are going to evaluate it at, we'll sample 2 random points from the transcript, and we are going to evaluate it at those 2 random points. So it's going to give us a different, like it may be 50, if 50 was our random point. It's going to give us the evaluation at index 50. Right?
Yes.
Is it making sense?
Yeah.
Okay. So now this evaluation at index 50, there must be 2 values from the layer beneath that if we perform some check over those values, it will give us 50. Right? This is 0 and 1, right?
Yes.
This one was 0 and 1, right? These 2 values may be 75, 95, like their indexes, right?
Yeah.
Their indexes can be, since this 50 is random,
Yes.
their indexes can be random,
Yeah.
you get?
Yes.
So normally, after we get it 75, 95, right? If let's say this is the index, right? Then let me put let's say the evaluation, right? So let's say the evaluation itself was, let's say 10, right? We don't know this gate. We don't know what the gate is. We just pick the random point. It may be an addition gate, maybe a multiplication gate, but the HDI basically for that layer has encoded it. You get. So if this is 10, this can be 5 and 5. And let's just say it was indeed an addition gate. Is it making sense? Is everybody following?
Yeah.
I'm not explaining to only. I'm explaining to everybody. Is everybody following?
Yes.
Okay. So it can be 5 and 5. That means this W, we'll call it W1, we'll call this one W0. Right? This is W0, this is W1. Right? It's still the same. This one and this one. It's the same polynomial. Just that when you evaluate it at 0, you get 50. This one, when you evaluate it at 50, you get 10. If you evaluate it at 1, you get 0. Is it making sense? Making sense, right? Okay. So, we are saying that there are 2 values from the layer beneath, such that if we evaluate that FVC polynomial using, let's say, 75 and 95, whereas our RB and RC, we are going to get 10. Is it making sense? Okay, good. So now, it's the prover that actually told us that if you evaluate W1 at 75, you're going to get 5, right? Which is WRB, where RB is 75, right? And the prover told us if you evaluate W1 at 75, you're going to get 5. is the prover that told us, so we don't trust it. Right? The prover also told us that if you evaluate W1 at 95, you're going to get 5. That's what the prover told us. Right? So since the prover told us these two things, we don't trust the prover. And basically, we know that we can get the values of layer Wi plus the values of layer Wi plus 1 from Wi plus 2. Right? So we know that we can get okay, so this is W2 now, right? And we need a sum check proof to prove this guy and this guy. These are now two sum checks. To prove that W1 evaluated at 75 is 5, and to prove that W1 evaluated at 95 is 5. So those are the two sum checks we now need.
So when you say two sum checks, you know, for every layer there's a claim sum.
Yes.
And the layer below it, you want to relate the claim sum of that layer to the FBC of the layer below it.
Below it, exactly.
That FBC is a polynomial.
Yeah.
The claim sum at the top is a value.
It's a value, yes.
Now, that is a subject problem.
Yes.
So when you say we are performing two sum check, it sounds like the sum checks are being performed on the gate. But from the explanation, the sum checks are not performed on the gate. The sum checks are performed on the layer at the claim sum of the layer at the top relating to the FBC of the layer at the bottom, which is one sum check.
Yes. So this is our claim sum 5, right?
Yes.
This is for the first sum check. Our claim sum is 5, and we need to get an FBC that will relate the layer below to this 5.
You know, the claim sum is not a point. It is like the polynomial on that layer evaluated. So if the way you point 5 here and 5 here is looking the claim sum as if it's coming from here and it's coming from here, the claim sum is supposed to be like everything evaluated on that layer gives you one claim sum that used to relate the layer below. But the way you point 5 here and 5 here is looking like the claim sum is coming from this each of the inputs.
You know, like, it's actually two different claim sums.
Okay. On a particular layer.
On a particular layer. One layer, but two different claim sums. One of the claim sums is W evaluated at RB.
Okay.
That will give us one claim sum. And W evaluated at RC will give us another claim sum. We need to understand that W evaluated at RB will give us a value. Let's not call it a claim sum first. It will give us a value. W, which is still this W1, evaluated at RC, will give us another value. So they are giving us two different values, right? But it's the same polynomial, evaluated at different points, RB and RC. But those two different points were gotten from the layer below.
Okay.
So let me just use an example with respect to this, right? This 75 might have been this index 75,
Yeah.
and this 95 might have been this index 95, right? And this guy now, we still need to prove just the same way we proved this one, that two things from the layer beneath gave it. We still need to do the same thing for this guy, but here, right? That two things from the layer beneath gave it, and also for this guy, which is this guy,
Yeah.
that two things from the layer beneath gave it.
That is two sum check.
That's two sum checks. So now, before our sum check was 2, right? Which is this and this, which is this 75 and 95. But once we go one layer below, our sum check blows up.
Yeah.
So now we need to prove that two things from W2 gave 75, right? And another two things from W2 gave no, this will not be 26 now, this will be 5, right? Because now, so let me bring in the 5 back, which is basically just this 5 and this 5, 75 and 95. But you know, these things are happening at random places. Like this guy, basically, when we use the randomness for this guy, it moved him
Yeah.
like way off the normal circuits.
Circuit.
Yeah.
Yeah.
So we're no more dealing with Boolean
the-
hypercube
yes,
values.
yes.
We're now dealing with actual random numbers.
Yeah.
Right. So now we have 4 different claims. Right? This 1, 2, 3, 4.
So that requires 4 sum checks.
That will require 4 sum checks. But our RB and our RC are still random values. So we don't want this blow up, right? That is why instead of doing a different sum check for 75 and 95, we reduce it to 1 sum check.
So basically, the number of sum checks. So this is the same thing I was saying. Sorry, I think. So this is a gate here, right?
Yes.
This is another gate here, right?
Yeah. But don't think of this as on the circuit, right? It's
Yes,
outside.
yes. So this is a gate here, this is a gate here, this is gate here, this is gate here, this is gate here, this is gate. So what I said before was the number of sum check is based on the number of gates in the layer. So this is 75, this is 75, which was the output of this gate, right?
Yeah.
And we are performing 2 sum check here to prove the guy below. Now here is another output, which came from this gate.
Yeah.
So which means we are performing 4. Sorry, I thought this. So which means we are performing 4 sum checks here, right? Because of the output values we have, which are coming from 4 different gates. So that's why I was saying that normally without the folding, the number of sum check we do will be based on the number of gates. And so your explanation is using the output of the gate, so which is kind of like similar.
Okay, I think I get it.
Yes.
I get it now. So it's just like moving this guy back here.
Yes.
Although we know like everything is moving
Out.
out.
Yes.
Yes.
Based on what you said before, so what Cass is saying now, it's only odd for when there is one output. What you are saying, it's only odd for when there is one output.
Maybe if there's more than one.
If there is, let's say there are two, from what you said before now, if there are two outputs, we won't do like claim sum we won't do some check for those two. We do for only one.
Okay.
So that means we continue to
Okay, you do for
for
if there are two
it won't be
outputs,
yeah.
You just do for
One.
one output down.
Go
Yes.
down.
Yeah,
Yes,
so
so
that
you
one
do
have
for
become
the
two.
second one.
Instead of it two
Then we
becoming
do
four.
that first one. That means the second one is correct.
Yeah.
Yes.
So it only holds for when what you are saying like that the claim sum is the same, the sum check is the same number of gates, like the same amount of gates on that layer. It only holds for when there is one output.
Okay, I get what
Do
you
it,
say.
yeah.
Because just like we ignored
It's still increased.
Yeah, just like we ignored
just like we
that one.
ignored this one
That time
and use
yes.
only this one now
Yes.
to go down. So if the output was
If there were like four outputs,
yeah,
we
it's
got like
just-
three of them.
okay.
Yeah.
But then with the correction of this one mean that this is now.
Yes, since we're like getting another fifth value that is representing all
But
four.
this one is still increased.
No, it will still keep increasing actually, but you know,
So
this is
that's
what it's
where
saying.
this thing now comes in, making it one.
This was what Carl said now. Like, let's say there were two outputs on this one. Then on the second layer, there will be 4 gates, which will mean we were doing 4 sum checks. But no, we'll only be doing 2 sum checks, even though there are 4 gates. But right, so what he said works for when there is one output.
Actually, there are two outputs here.
Then still one, we just added that 0 to make it a.
Yes,
Okay, let's say there were 4 outputs, we need to add 0.
Yes.
But
so,
then we still do 2 sum checks the next time. We won't
Yeah,
do
so-
8.
like what he did now is like, that little 0 we added just give us 2 outputs.
Yeah,
with
something like
the
that.
point that
The
it
reason,
doesn't exist.
the reason why it will happen is because for the first output
We are using
always passing
one
just one
random
down
challenge.
game sum and this thing to the sum checks. That's where you're starting with this thing.
So that's why it's like increase to 2.
Yeah, exactly.
It
But
won't.
if we went that route, if we went
You guys implementation. Right?
no, I'm saying
No, normal.
exactly. And you know we've changed
Normal
it.
this thing.
But if we went that same route of alpha beta folding from the first, you would have like originally more than
Yeah.
the reason why you always like
Start with
from two
1,
subjects
2,
because
4 is
from
because
the
like you
initial
get
layer
some
you're
value.
like basically sending just one like
Regardless of how
challenge
many
exactly,
outputs we
regardless
have,
of
it's only one you're
outputs,
starting
it's
with.
only one.
So that's
So now, based on this stuff now, so what does the folding do?
Okay. So now, like, well, sorry, is everybody following?
Yeah.
So, I I said, "Duh." You see the difference? Okay. The alpha. This is 11. Are you How am I doing? So, okay. So based on this, right, instead of us to have 2 sum checks here, we fold it to get 1. So we collapse it to get just 1 sum check. But that 1 sum check will still need to prove that it came from 2 values we need, right? Which should give us another 2 sum checks again. But when we get these 2 sum checks again, we fold it again and basically come back here. Right? But down though, I'm just
and we still have one new one again.
like this.
Yeah, something like
okay, yeah, exactly.
keep brush down, but then we bring it back.
Like the 2 of them will give us 1 here that we now need to prove came from the layer below. Another 2, right? We fold it again.
Do we need to
Yeah.
fold? So, if we fold the 2 here, it becomes 1, right?
Yes.
Which means the one below will give us 2.
Yes.
Now, if the one below gives us 2, we fold it again to get another 1.
Yes.
Okay?
So we just keep, like, whenever we get 2 sum checks,
Yeah.
we don't want to do those 2 sum checks.
Yeah.
We reduce it to 1 sum check and do that 1 sum check. But whenever we do 1 sum check, we're still going to get 2.
Yeah.
So we reduce it again and we just keep doing that.
So, so you fold, it gives you 2, you fold again. So it's not like your sum check doesn't stop until you've gotten to the end.
To the inputs.
Yes.
To the input.
To the input. Yeah, makes sense.
And when you get to the inputs, it's still 2,
Yeah.
right? But now, no need for sum check again,
Yes.
because the verifier has the input polynomial.
Yeah.
So the verifier just evaluates it at WB, RB, and WRC,
Yeah.
and gets.
No need for some check.
When you get to the last layer,
You still do some check now to get the hours.
That is
Okay,
second
okay,
to
well,
last
in the
layer.
layer before that one.
yes.
Okay, are you done?
Hey, Francis, will our current implementation work for more than for output that is more than 1?
Yes.
Not as getting 1. So this output is actually a polynomial.
Yes.
So evaluating it with one random challenge to get one value back. So it's always going to be 1, regardless of how many you put into it. Yes.
But you need to also take care of that in the code. Like,
Yeah, how many
Cass was saying.
how many inputs will you now put? How many values?
Yes. How many random challenges will you now sample? You need to now be getting, instead of just taking it as
1.
1, you need to get the number of variables.
Yeah.
Yeah, use that
To generate all the
yes,
random
to generate
challenges.
your random challenge.
So for that second, if it's 2 now, you now for the first time, I know it's just Shamiro, you do like the first polynomial.
Yeah.
Then over second one, like for the out 2, if there are like 2 variables or 2 inputs and 2 variables.
You like if there are 4, right?
If there are 2, sorry. No, I mean 4.
4 evaluations, right? Which is 2 variables.
Yes.
So you sample n, which is sample 2.
The first one. Like I'm still have to get it out.
Yeah, to get the R.
You
You know if there are 4 values.
Mm-hmm.
So this is 0, 0, 0, 1, 1, 0, 1, 1, which is basically 2 variables. So in your transcript, you'll be sampling 2 challenges.
Yes, in the transcript, you have to turn 1 challenge, right?
In the transcript.
Yes. You turn 1 to the element to the challenge.
Yeah, but we have, that's why Wilson said you guys should add a function to your transcript that sample n challenges. Yes.
What is the purpose of that? Can we possibly do first one to give us the hour one?
Then put it back.
Yes.
Does that work?
Yeah, that one. So that you probably do like a for loop
Yes.
and sample multiple challenges. But
I did that because you don't look his back.
so like that may now affect like the code readability.
Availability.
Yeah. So inside your code now you'll be doing a for loop to sample 2 challenges when you can just move that to the transcript and call sample n challenges. So let the for loop be in the transcript. So that your this thing will
Any
be
number of variables.
yeah.
Okay,
For him.
yeah. Thank you.
Yeah, thank you. Yeah, I need to watch the So does it make sense?
So what you are saying now is that if we, let's say we have a circuit, then we now decide that will only be going using two leftmost down. It will prove the full circuit.
If you pick your random challenge to be 0, that is when it's so. But picking your random challenge as 0, you're shooting yourself in the leg.
I know I found why you are saying pick random challenge as 0.
Like, if you pick, let's say this is a circuit.
Yes.
If you pick your random challenge as 0,
Are you writing?
yeah.
Okay.
So if you pick a random challenge as 0, what you will be proving is basically this circuit, right? If you pick a random challenge as 0, because once you pick this output, it forces every other thing.
Yeah.
It forces every other thing, right? So this is basically what you will be proving, and it's not secure, right? Because the program might have lied on these values.
Okay. I only be wait. So what you're saying is, if I pick any point, let's say I decide that I want to start from the top, going left, then those two there, and I go left again. So I'll end up at 1, 2. Like the input I'll end up at are 1, 2.
1, 2.
Yes.
No, like once you pick this guy, like if your random challenge is 0, that means you're picking this guy, right? Then you need to prove this 2. If you don't use a random challenge to merge the both of them, if you want to do 2 different sum checks,
Yes.
that means you're going to do sum check on this guy and this guy,
Okay.
on this guy, right, and this guy.
Yeah, that makes sense.
Okay, so it's going to
I thought what you were saying was that we can only pick one side and just do some check there and be fine. That's what I wanted to ask. Then also for that degree, that's degree now, that polynomial, the layer, right? You know that we can evaluate the layer using random challenges. And when you call partial sum, partial proof or partial verify, you pass in the clean sum. I never pass in clean sum. No, you can still get the claim sum.
Yeah, you can
inside
still
now.
get the claim. You
Yes.
can get the claim sum 2 ways.
That's what I'm
Right.
trying. That's the point I'm trying to make. So
Yes, you can
I
get
never
it 2 ways.
evaluate it with you. That's my
Yes.
point.
You can get it 2 ways. That's basically the same thing Rohima was asking. So you can get it 2 ways.
Sorry.
Okay. So you know that we have alpha WRB, right? Plus beta WRC. Right? You can get the claim sum like this. Right? Another way you can get the claim sum is by basically on the other side of the equation, where you do your add or alpha times add I ABC, right, plus beta, how should I call this? I call it R.
R1. So
Call it
don't be
R1.
R2.
Yeah, so the other one can be R2. So plus beta times add I R2 BC, right? And then this will be a new add I, right? Then we multiply it with WB plus
I thought you want to get
WC.
both of them and check if they're okay.
Yeah.
Yeah, but like you can do it this. Let me just outline the more like. more like R1 this right more like R2 this. Okay, so you can get the claim sum this way, right? Where the prover will evaluate the W polynomial at RB and the W polynomial at RC, right? And send it to the verifier. What the verifier does is alpha times WRB beta times this thing. You can also get it this other way, right? Where the prover sends W evaluated at B and W evaluated at C, right? So that the verifier can do WB plus WC, WB times WC. And then this other part, for the verifier to do this part, the verifier will now need to evaluate add like evaluate this guy at the sum check random challenges to get a constant value for this guy, and evaluate this guy at the random challenges, the sum check random challenges to get a constant value. Then multiply alpha times that result plus beta times that result to get this first part. Right? And then for the second, is it making sense?
You know that was flash. Like, it's not about that it's you not doing from scared claim sum.
Yeah. So what you said you were not going to get the claim sum was, if I'm not mistaken, it was this.
Yeah, I was not evaluating the left at all.
Yes,
Yes.
and so I thought this is like the test. Because I've
So-
already said you just check.
This is not the check.
You don't just do that every day.
Both of them are
How are you getting the
power.
claim sum for the
Some
verifier?
When you pass in the right hand side, that's basically your FBC.
Yeah.
When you now reduce it, your first in vehicle is going to be 3 values. You
But
add the
you-
first 2
that's not
values.
some check.
That in my partial, you're supposed to pass the claim sum that you evaluate on the left hand side to your partial sum check.
Yes.
Yes, now. So inside the partial sum check now, when in your first in vehicle, when you reduce this FBC, you're going to have 3 values. If you add the first 2 values, that's your claim sum.
Yeah.
That's
Okay,
But that's
it.
going to be for the verifier to do.
For the
and that's what I'm saying. You only need it in the verifier. You don't need it in you don't need that claim sum.
You don't need it in the prover.
Yes, now.
The prover needs an initial
So
Okay.
the reason why I
And an
passed
FBC.
my basically is for my transcript I'm committing both the claim
Claim
sum
sum,
and the univariate. But most people don't commit their
I commit mine too.
So the
But
thing
even
is,
the initial
the
claim
thing is, it's just the
Even the
pattern.
initial claim
So
sum.
it's just a pattern. If so, I noticed that.
Because at least the initial claim sum is important to pass into your transcript.
So the initial claim sum, that one is like, that's what the whole protocol is basically built upon.
I feel like passing something to
Right.
the transcript is just a unique way of creating randomness. Which means if you're passing claim sum in your transcript in the verifier, in the prover, you have to do the same in the verifier so that you'll be able to get the same claim sum. So anybody that is not passing that claim sum in the prover is not expected to pass it in the verifier. Else, if you pass it to the verifier, it will generate a different randomness, which will not equal to this, because in Oba's code, in his verifier, is in his prover is passing the evaluated W poly and WB and WC to his transcript, which gives him a unique randomness. So he's also doing that in his verifier based on the unique evaluated WB and WC that the prover sends. You understand? But me, I'm not doing that because I can squeeze twice. I can squeeze and squeeze again. That's double squeezing. Wisdom mentioned that you can squeeze more than based on the way based on based on based on the way the transcript works, because when we fold, we append the previous stuff. So if you squeeze twice, it will still give you random stuff. So I believe that the process of appending is just a way of getting your own unique randomness. So if you're not putting claims on, you have a way of getting your own unique randomness. But me, I'm actually passing claims on.
But we should not be picking what we want to pass and what we shouldn't, right? Because that can basically, in short, when you hear Fiat bug,
My head is that.
now yeah, you be.
That's what it's starting. That's it.
So you get. So you should not be picking what you want to pass.
You know which one is right pass.
Like anything the prover is meant to send to the verifier must be in the transfer.
And that alone means only that, not extra.
Eh? If you want to add extra, you can add.
So that double
That's
that double
Yeah,
That's for
randomness.
security.
Make sure everything
that double
is
squeeze
right.
we are doing is not
Whatever
really
you
good.
No, the double squeezing is still okay, right? Because we basically said that in that your squeeze function,
Yeah.
you should absorb,
The new value. So it's like the same thing
so
actually.
it's almost the same thing.
But which one is the best? So we should append the evaluated W polynomial. Since it's something the prover is giving the verifier, so everything will be in the transcript. For more
Yes,
security.
everything like for security, everything should be in the transcript,
Including the initial crimson.
including the initial claim function
Because
in the
this
transcript.
alpha is like the initial crimson for each sum check round
Yeah.
before it generates the univariate polynomial. So
Well, I think I understand, but
No, said is not
No, say
calculating
no.
that. How?
so your subject proof basically has the initial claim sum and the round produce. So he's saying, like us now, if we calculate this initial claim sum and we pass it into the generic proof for the partial prover, right? All the partial prover does is just to add that to the subject proof to send to the verifier. We really don't use that initial claim sum in the partial proof, right? So he's saying that instead of passing this initial claim sum
From there,
outside,
yeah,
you
he
know,
can
basically
get
the
it
initial claim sum
inside.
exactly. The
but he
initial claim
still
sum-
adds it right after getting it.
Yes, exactly. He still adds it to the subject proof. So the verifier just does what he needs to do with the initial claim sum.
well, I
So that's what
absorb
he's
my
saying.
We are
into the
committing our own
transcript.
initial claims on it.
No, I'm not permitting initial claim.
Yeah, we are committing my
Yeah.
initial claim.
Why?
I'm not just
My
giving
initial
it.
claims.
I'm not just passing it to the proof. I'm committing
Yeah.
it's part
To
of
the
it.
transcript.
No, I'm just committing.
committing.
Wait, is it not just the initial polynomial you are meant to commit to? Are you committing the initial claim sum?
Yeah,
Yes.
you should.
Yes.
Even in normal sum check.
Even normal sum
Our
check.
sum check.
Yeah. Even the normal sum
Something
check.
like I not passing to
I don't
something,
think
just deliver it inside.
inside and put it with the invariant point inside the transcript.
Yeah, I understand.
Actually,
Okay.
you can have it before sending it to the sum check, or you can have it
Oh,
in
yes,
the
you
sum
are.
check and absorb it.
Should we see and project it that way?
Or is it how it is?
The thing is,
Like-
the partial proof, you don't even have initial proof.
No, he meant claim sum.
Your partial proof, you don't have initial proof. It's just a claim sum that you're passing.
I want to confirm.
The initial poly,
Then
that is the
Yeah.
polynomial for the output
Yes,
gate.
sir.
No, like the
no, like no, not like normally in our basic sum check, we commit the main polynomial, like the main polynomial. But this one we don't commit the main
Yeah,
polynomial.
that
It's
is
just
okay,
some then
yes.
start
The main
committing
polynomial
the
is-
round
Exactly.
poly.
Yeah.
Yes, and that's
The main pool doesn't really
Yeah,
exist
just
still.
that way you
some-
mean.
Doesn't really exist in this
So,
one.
I want to confirm. You are saying we should commit the evaluation of W, that is WB and WC.
is it W or WB?
WB and
Like
WC.
The
W0.
evaluation.
The evaluation of W0 at R0.
Mm-hmm.
We should commit to.
To the transcript.
Okay, no,
That's the initial
that's
claim.
the
So.
claim. So I'm not talking about that one. I'm talking about the WB and WC now.
The evaluation.
That the
Yeah,
prover is sending it to the
evaluation.
verifier.
We should also commit it to the transcript.
Yes, because the prover sends it to the verifier in the
Mm.
play.
I'm not committing on
The prover sends
Wait,
it.
I
wait,
don't get
did
that
the G
part.
wait, is that in the GKR?
I don't get that part.
That's in the in the GKR prover and also in the verifier. So
GKR program send what?
this value W evaluated at RB and W evaluated at R.
You commit it, like you absorb it into the transcript.
Yes.
Every-
That's your tuple now.
Yeah.
Yes.
But
Those-
then I just put it in my
In your
GKR.
No, you should add it to your transcript. See, it can get crazy. You get so like sometimes keeping track of, especially maybe when you want to write tests for your code, and by the time you want to
I just copy on test.
by the time you want to write tests, all the adding to transcript something like you may just be this thing may be failing because maybe you're adding something before another thing or
I forgot to
Okay.
provide something.
yeah.
Mine was failing because I was using the same transcript.
Yeah, that was the same thing that
It's
you
the same
did.
transcript now.
No, I used the same transcript.
Like in
all
both
throughout.
prover and verifier.
Yes,
that was the same
So
issue I
like,
had.
I instantiated the transcript and passed it to the
Pass it
prover.
so
The prover used it all through both in Sumcheck and in GKR. But when I now created my when I now called verified proof, I should have
Like that's a new one.
but I passed
It's a
the
part
same
of
oh,
the
the
same
sensor, oh.
So it does not produce
Ah, it's going to be
I
crazy.
face that issue.
So I
Oh
checked.
my, how did you debug that?
No, like I would check now. Like I knew that normally hashes are supposed to produce the same
The
value.
same value.
So immediately I saw they were producing different value. I just said, okay, it should be the truth.
I think that's the same this thing you're getting the whole sampling different.
So wait, you said we are
Everywhere.
committing
That would be
WIB,
nonsense.
WB
It's the one that
and
was
WC.
on
WB,
Evaluated.
The
WRB.
other is verified.
I mean, is it WB?
Verifier stress.
WRB.
WRB and
Like trap gain have been approved.
Yes.
We don't really have to verify.
Why don't?
Hmm? Because if you don't commit to it, the program can say, if the program gave you 5 and 7, you can say it's a lie, right? Not give you 5 and 7. I gave you 20 and 14.
Hmm. Hmm.
90 like.
No. See, as simple as that thing sounds, it's like
Something that can happen.
major because it looks like it's nothing.
But it can always happen
Yes.
easily.
But still,
On scale. Still on scale now.
right. I mean, the fact that we are performing some check here, I don't see how they can lie about like DWB and WC and not get caught like
Not
that.
get caught. It's a shock.
People can be very smart.
Like,
And face value.
like you may think it's just this, but there are people that
After the like
can
find
use
the way to
maybe memory corruption. Like someone can decide to use memory corruption
No
to
money.
mess things up for you.
Yeah.
You get. So also we are thinking about it softly on the surface. But everything is running on a computer. Right. And somebody can basically write a code that modifies a particular memory cell in a computer or modifies a particular register on a computer and generates a different value. Right? So so that's just it. So anything that the prover sends to the verifier, we need to commit to it. We need to add it to the transcript.
So those is the waivers already.
for those that have not finished, hope everything is getting clear. Right? And yes, even those that are finished, like everybody is learning, right?
Yeah.
Okay.
Okay. So back, we stopped at this place.
So what's time?
To past already, 2:10. So there's still like a lot left to do.
Let's see it.
Yeah, we've not entered some check yet. And then verify.
That's the first.
Okay. So after we've gotten our FBC and our W police, next thing is to do our sum check itself. That's where we get the round police from, and the other things we need in our proof that we are going to send over to the verifier.
Let's check the record.
Okay. I think it is. So, in this place, this one I'm running the proof. My partial proof and partial verify. I called it GKR proof and GKR verify. Let's continue from there. Yeah. So it takes the claim sum. The provider knows the claim sum actually. That's M0 for the first round, but for the other rounds, it is the merged the one with WB alpha and beta. Sorry. And then this is the FBC polynomial that I called composed polynomial, and then the transcript itself. So it calculates number of rounds to know how many times it's meant to do. It's meant to be 2, but I guess our coding it to be bad, so just leave that. Then proof polynomials and then current polynomial so we can notate it. So we get our proof polynomial. This is the main change we're actually meant to make to our sum check. This getting the proof polynomial. So the one we did before, to get our proof polynomial, the normal sum check, we just take we have where it is 0 we sum it, when it is 1 we sum it. That's our proof polynomial. But in this one, we do it for all zeros, all ones, and all twos. So we can't really divide our two since 2 doesn't exist on our Boolean cube. So instead we do something like this. We go through each point, like we partially evaluate each point. We partially evaluate the stuff at 0, 1, and 2. Then reduce and sum. Our reduce function is just doing elements wise either addition or elements wise multiplication. That's what reduce is doing, and then we sum it up. So whatever we get, whatever we are going to interpolate, because we are getting like summed points. They're not really points. They're not really x points for your polynomial. So you just need to like interpolate that to create the actual unique poly that would send. So yeah, I'm getting that one and then appending it to my proof polys, and I'm getting a random challenge for B and C, and I'm also passing that. And so as we do a normal sum check to that, we reduce the polynomial after we get the first random challenge. That's what is happening here. So like we know we're doing for like fewer variables next round, and that's the proof. That's the claim sum, the random challenges, and the proof polynomials. Then the GKR verify, that's like my partial verify before I go back there. It is taking those polys, those round polys.
Is it making sense?
Yeah.
So yeah, the verify is taking those round polys. Normally we're meant to like pass proof here, the way it is normally, but I'm just gonna do it like this. I removed those specific things I need for GKR here from the proof. So it's taking the round polys, the claimed sum, and the transcript also. So this is basically just now checking if two of them are equal. The round poly at evaluated as 0 and evaluated as 1. If you sum it up, is equal to the claimed sum. If yes, if no, just fill at that point. Return false with 0 everywhere. If yes, go to the next one, like do the next point until we get our RC, which is the last one, where we're now meant to actually do our what's it called again, oracle check, where we check if RC evaluated at R2 is equals to the F at R1, R2. But we can't do that. So yeah, it's part of the things that we.
GKR verifier.
No. This is some check. Yeah, this is like partial verify. Just call the GKR verify, and GKR proof is partial.
Yeah.
And we name it. So the things we're returning from this one, we're returning if it's verified. That's if it didn't fail during when it's checking 0 and 1. Then the final claim sum, that's our FC evaluated as R2, and then the random challenges, which are R1 and R2. That's what your verify will return back to the verifier in GKR itself to now do the oracle check. So back here, so when we run this, we get our get a sum check proof object which contains all those proofs. So what I'm doing in this loop is mainly just computing the proof, actually the proof that we're going to give to the verifier and the values for the next round. That's just what is happening here. So this is getting the next polynomial. That's the next W polynomial. It's turning it into emotional polynomial. Sorry, we've gotten into our WI. But then it was my implementation. It was only evaluation points, so I'm just turning that into a multilinear polynomial. Then I'm splitting my random challenges into RB and RC. That's what is happening with these two lines. So then 0,1 is that big B and 0,2 is big C. That's the W poly evaluated at RB and the W poly evaluated at RC. That's why I call 0, 1, 0. I think. Huh? Since I was doing one explanation that wisdom called the 0, 1, 0, 2. That's why I use that.
So when you are splitting your random
yes. Yeah, because it's going to come back as an array of multiple points. So I'm splitting it to know we're meant to do add die at one RB, add die again at RC again. Sure.
Sorry, like I don't get a result here from that verified, GKR verified.
We're doing GKR verify to get our round police that we give to the
Where
proof.
are we? Where is that?
This is that's it. So this one is just yeah this is GKR proof.
No, the one I was talking about is GKR verified.
No. I only explained it since I was in the sum check file. I just said what it was doing. We've not yet gotten to verification yet. So this whole if block, the reason why I put this if statement here was so this thing does not do it for the second to last layer. The verifier does not need us to send anything to him. Not us. The verifier does not need the prover to send anything to him for the second to last layer. That's the last layer actually, since he can compute it himself with the inputs. Hope there is no confusion anyway. So that's why this if statement is there. It can actually continue and there will be no error, but I just feel it is like wasted resources. Okay, I stopped it.
And then the protocol is supposed to use the inputs for the last.
It will still actually calculate correctly. To use the inputs to calculate it and still send the ball. The verifier won't use that. The verifier will use inputs by himself. So so this is just that whole process, getting our big B and big C. That's my 0, 1, my 01 and 02. And then I'm updating my current random challenge for the next round. And of course I'm appending my 01 and my 02 and the B, that's W evaluated as RB, that's 01, and W evaluated as RC 02. So I'm appending all these ones to get my alpha and beta also. And then I calculate the next claim sum. Like I'm updating it for the next round and the claimed evaluation. I'm just pushing it. So hope this one is clear. That's all I'm proving. So hope the thing that's happening there is clear. I'm like rushing because of time perception again.
So you're sending this phone and you to the transport.
Sorry, what did you say? What did you say? That's WRB and WRC, yes. No, we're sending those things to this thing. So now verify. This is what the verifier will do. He's taking the proof. He knows the circuit and the input, they don't know the intermediate stuff, and then it's taking in the proof also. That's the one you got from the prover. So transcripts, getting the current claim, that's the M0. This is like for the first round, getting the M0 and that first random challenge, so you can start his own verification process, his own sound check. So and then alpha and beta just random this thing. I'm also keeping the previous random challenges here also. So yeah, then reversing because of the way I created my stuff. So we start with getting we first verifying it with the sum check. That's what is happening here. And then this is our first check. Did the sum check fail? If the sum check failed, return false at this point, like just stop the whole thing here. The sum check will fail if the round pool evaluated as 0 and 1 sum together is not equal to the claim sum. That's why the sum check will fail. So this is like the first check. Then we get the random challenge. That's the RB and RC for this layer that we're on. And we also get the O1 and O2, so we can calculate we can do our final oracle check. So for this one, I created okay, I'm dropping. So in this place, you notice I have like if we're already on the last layer, then just use the input. You don't need to like take it from the proof anymore. That's what this guy is doing. Okay. So and then after it does this, we calculate, we use this get verifier claim just to evaluate that whole W plus, just to get his own this thing, and then we're not. So it's like there are two functions, to one that does for alpha and beta, the other one that does for when there is no alpha and beta. That's the first round. So and then this is the second check. So it checks if the expected claim is equal to that's the F evaluated R1 and R2. If it's equal to the FC R2, then if it's not, return false. If it is, update everything for the next round. So if everything should pass, including this one that was done with the inputs, if everything should pass, then it means yes, the prover was correct and not return true. But if any of these steps were wrong, it have already stopped the function and that returned false already since. So that's what we have verification. Is there any question? Do you understand it?
Anybody have any question?
This gets very powerful. What?
It is just that one is just calculate. It is a very, very small function, but I just separated it not to put too much in my this thing. So it is just evaluating. It's getting your R die, your W. It is doing that. No, this stuff is jumping my head. So it's just basically calculating this stuff like your AR. AR is your R die, evaluated at R1, RBRC. Then your claim, your B and C, add it to your MR, which is your model I, B and C. This was what it could not do before. This was what the verifier could not do without requesting for these two guys. So it's just calculating here, so that this one is not really, there's nothing much going on in this one. So this one is taking in beta and alpha. So it's just doing alpha times B plus alpha times C.
Alright, so this particular function, this get met verifier.
Okay, this one. And the two of them.
The other one.
Yeah.
So this is like the heart of your verification.
That's the main.
Without these two functions, you cannot perform your verification. The reason is because normally, the verifier is not supposed to know the W polynomial. And normally, if the verifier wanted to perform the check for every layer, what the verifier will do, the verifier will get the W polynomial and evaluate the FBC polynomial himself. The value he gets, he now compare it with the claim sum,
yeah.
with the claim sum to check if it matches. If it doesn't match, it's going to return false. But now, the verifier doesn't have access to the W polynomial. So the prover is going to send the verifier the evaluated W polynomial, right? When it's evaluated, the value. So that stuff the prover sends to the verifier receives it, uses it now because the verifier has access to other more line. The verifier has access to the evaluated, so it will use it now and compute a value that when you evaluate WB normally is going to give you. Use it to compute that value. Now use that value to now compare with the claim sum. So with that evaluated WB and WC, the verifier can still use it to recompute what he would have gotten when he evaluated SBC polynomial. So that is what he's now using to check with that claim sum to see
check.
if it matches. So that is what this particular code is doing. So it's different for when you're in layer 0 and when you're in layer other layers, because layer 0 we don't need alpha beta, but other layers you need alpha beta to recompute your LBC polynomial. So that's why both functions are separated.
Can simply say this is evaluating your FBC polynomial with the things the verifier knows.
So basically the oracle check.
Oracle check for each.
Yeah, so that this function, it returns a value. That's the like I called it expected claim. So what is it like expected claim is like, this is just picking which of the two functions to call. So now it checks the expected claim is equal to the one that came from some check. That's the FC evaluated R2. So if it is not equal, fail and end the whole thing there. If it is, continue till you are done. Continue like to the final layer, and then if everything is correct, true.
So like after you do the oracle check for each layer, that's the end of the
Yes, as long as the one as long as you've done the oracle check with the input layer and that one is correct, then you are certain every other thing was correct. So is it clear to everyone? Or is it clear, right? Doesn't make sense.
Right.
Dean, is it clear?
Yeah, it's a lot actually. What's that? It's a lot, but okay. So with what we've seen today, with what we've learned today, let's go back and work on our codes. Then tomorrow another person will be doing this thing.
I have a question.
Okay.
So concerning the appending of the evaluation point, right? So you said that both of them have to commit to the evaluation point, right? But basically, the prover is still the one sending the WB like evaluated and the WC evaluated, right? Because the verifier does not know.
Yeah, the verifier does not know.
So what is the point? If like the value that the verifier is committing to is the same thing the prover sends to it.
Yeah.
Do
So
you
like in as much as it's the prover that is sending it.
Is it that you don't want the prover to come later to change that value?
To change the
Okay,
value.
that makes sense. Because I was wondering like if both of them are committing the same value that one source knows, like what's now the point of like
Yeah. But it's just like, I think of it like a polynomial commitment.
yeah. So you know that this is what we've been working with.
Yes,
since
this is
the
what we're
start
working
of
with.
the
Okay. So, in the absence of any questions, we hope we've been able to convince you and not confuse you. Eh? Okay, so
Not too late.
I'm going to come back tomorrow. Thank you, Oba.
Thank you, sir. I'm appreciating you.
More blessings, more knowledge.
Okay. So with that, we'll be calling it a day.
Is there any treats?
Treats.
Risky.
One guy's worried with
It's not risky, that's really that's
There was a paper yesterday.
Abby.
Which one?
I just